Welcome to your third lecture, A Basic History of Computers for Comp 3309. So before this, we stepped into the course talking about some kind of epistemology and ways of knowing that people interact within the world and how we understand society and ourselves. In the second lecture, we went more over some typical views of technology and what is information technology, and talked about different perspectives people could take on either side. Now, before going further, we're going to go back in time and do a very basic history of computers. And this will not cover everything of the entire history, informative and in-depth. We only have like one set of lectures for this, so I want to give you a basic overview to give you context of, well, how have things changed in regards to technology for computers and information technology as it relates to the field within? So not just technology in general society, but what has happened with computing technology and where did it start as an understanding versus where it is today with what we view as common knowledge when we say the fact of what computers is now and our typical kind of worldviews we may be holding today versus, well, what could have they been before with what computers were and how have things changed over time to give a little bit more context to what has been going on. Okay, so we talked about technology before, and I mentioned the idea, well, information technology, IT, something that we're used to hearing as a term nowadays, but understanding, well, what is the real difference of that? And we have to know that for information technology, the idea of storage and retrieval of information and computations doing work with it is not a new solution. It's not like we've had technology and then information technology was then born later on. We've always had information technology. It's just how much was it associated with electronic computers and computer science, the computer world, and the business world versus, well, what does it mean? Because even the idea of language is a form of technology that we use to manipulate and interact with the world around us and communicate with other people. And through that, we have to have ways of storing it, of retrieving that information, of using the data that in the world that we're in now. Because, like languages, we speak it, we write it, we read it, we retrieve it, we listen to it, text-to-speech, whatever. It is a form of information technology that you work with. And so this storage, retrieval, and the use of data is not new to our modern world. Like we as humans have had a need to compute this idea for a very, very long time. Of the storage of information once we started to having to record things, once we started to have to communicate it, and how that's done in different ways between different cultures. And this relates back to the epistemology of like, well, how are people interacting and gathering their data? When does that happen? Is this cultures that are oral traditions with people and that social interactions? Is this recorded material where then, just like this video as you're listening to it now, is done at a later time from when I am physically recording this? Like I'm recording this today on January 23rd, 2022, but I don't know what day and time or in the future when you're doing this, but you can now have this distance in time that's different from an oral, like an oral culture of communicating this where you need people there in person. And you're listening to me, but you're seeing this medium. So this is not new as an idea. And so the storage and processing technologies, we can say to break it down, have gone through 4 distinct phases of information technology development. And we're going to go into more of the mechanical devices here and physical environment of how it's changed, not into other forms. So we're leading up to more about the history of computers and where it's come to. And thinking of 4 distinct areas of A being pre-mechanical. So this being that storage of information where there wasn't a mechanical moving part physical device that was part of this, then transitioning into more of where mechanical devices started playing a role, where you have gears and cogs and things that change, but then into electromechanical, getting closer to what we're used to, where it's a mix of moving physical parts, but also electronic signals that are going through an actual system, to finally what we're used to nowadays predominantly is those electronic devices, where everything seems to be digital, those ones and zeros and signals of storage within medium that we're used to interacting now. And we have to think, well, how will this shift through these 4 phases of history where they all played a role in what we have as modern day computers. Whereas there's other cases of like society, politics, and everything else that played a role. But on the physical technology side of this pre-mechanical, mechanical, electrical, mechanical, and electronic, playing a role in like in the development of what is information technology, how is it used, and how is it changed over time. So I'm going to go into that today, and that's where you can see like this is a lot of history for stuff and can't be done in just this one video for however long it ends up actually being in this one set of slides. But this is to give you a general feel of it for future discussions in relation to more about computers and information technology and society and the roles vice versa that it's played. So a beginning point for context. So even starting just with the word computer, because you probably have an image within computer. There is a specific image in your head of what a computer is based upon our interactions that we have today. And that is not what the word computer actually ever was. If you look into the etymology and the previous history of this, you can go further. If we go back to roots, if we're going with like English languages and going to Latin derivations of this, the word computere, I really doubt I'm saying that properly, but I'm making an attempt. It means like arithmetic, accounting, or reckoning. And the Latin word computere itself comes from the Latin com, meaning with, and Latin putere, meaning to settle, clear, or reckon. So in ancient Rome, at least to compute seems to have meant more or less something like to settle things together, or maybe to reckon with something. So reasoning and logic. And this is my understanding from it. And that's that beginning idea of computer, where we're not talking about the electronic device that we use within our phones that are embedded into everything else around us. We're talking about something is that bringing together, to reckon with logically, to get to a final actual result. We're doing something. And this is that beginning prehistory of what we're working with. If we go with more of a modern definition, pulling a definition from Oxford Dictionary, so going from way, way back in the day, before anything, so pre-electronic, pre-mechanical, all these kind of things to a definition of what could be a computer, to somewhat that fits a little bit better today, so the wide two spectrum of these, and looking at the Oxford Dictionary definition, is that a computer is an electronic device which is capable of receiving information, so data, in a particular form and of performing a sequence of operations in accordance with a predetermined but variable set of procedural instructions, so a program that is running to produce a result in the form of information or signals. And so there's a lot of key things in that definition that you have to pull out. The fact of one being that the modern day is saying electronic, that electricity and signals play a huge role. We still have the idea of storage of data, so we're still in that information technology realm of we have that storage. We have to have retrievals. We have manipulation of it, that we also have data that represents actions that should be taken by the machine, which is a program, and it's a predetermined set of actual instructions, and this is where programmers come into place. So your computer scientists, your BCIS students, anyone else who's creating programs that then manipulates that data and results in some form of information or signal. So you're thinking like audio signals, the visual that you're seeing right now, all the programs that have come into place, like I'm using PowerPoint and I'm using different screen recording apps to deal with this, and all of these things are dealing with signals and data in different ways, but in electronic format. The same way that you're viewing this video at some point in time later on is these signals have been sent. And that's a key thing of what we expect today, some kind of machine, that electronic signals, the data, that the fact that there's programs that are stored on it that manipulate that data for us and have different ways for that information to be presented back to us as signals that we kind of just take for granted. Now, these are the two spectrums, the just reckon with or bring together, to no, a computer today as a definition, as the word has changed within society and what we view as common sense when we say the word computer, is defined by this previous history and where we live now. And the question is, where could that be in the future? Like, what could the word computer actually mean in the future if we think that's going to continually grow, or is it still just going to be electronic, or is there something different? I don't know. I don't research that. But if we step back in between those two definitions, and before the age of having mechanical, electromechanical, and actually having like fully electronic, the term computer was actually defined as being a person who makes calculations especially sometimes with a calculating machine. So you have to realize that earlier times, the term computer meant people. It meant society and actions you're doing and doing calculations. One, just reckoning earlier on. Two, later on, doing actual calculations, and people were part of it. So earlier history, when you talked about a computer, you were talking about a job or a person, just as you would say a manager or a secretary or a cleaner. You were talking about a job, an activity, a specific action that a person did. Whereas now we are talking about full digital today, and so just those terms have different contexts and how we understand around that and relate to society. And even this beginning separation of the word computer from society to being electronic device and separating from ourselves and thinking it's not us, it's this separate technology, well, that changes. And like, what does it mean when we still view that we are interacting together, but the fact that even a term computer has changed over time? So the discipline of computing, nowadays, if we're talking about electronic devices, and we're talking about those ones that have programs and storage, and this is people who are in computer science, software engineering, engineering that deals with like more on the computer side, and the BCIS students, this is the discipline of computing is the systematic study of algorithmic processes that describe and transform information, their theory, analysis, design, efficiency, implementation, and application. And the fundamental question underlying all of computing is, what can be efficiently automated? So this is the study of computer disciplines, and this is where there are all these different fields that you have computer science, you have software engineering, you have our BCIS degree, like Bachelor of Information Systems, and all this range of how to efficiently, and what side is it? Is this purely the algorithmic automated way that you see in computer sciences? Do you get the software engineering, the processes that we follow through using information to develop software? Do we get into business systems and the access and analysis of information to do work for us and understand the world around us? What does that mean? But that's still that information technology, and then the role that people, mechanical and electronical devices play within this, and our study to make that better. And all these disciplines of software engineering to like computer science to BCIS have subdivided fields that you go further. Human-computer interaction, of how we interact with the actual computer and the devices and the layout of stuff, to like theoretical areas, to design and efficiency of algorithms, to just how to manage and run projects itself, let alone the security of information and intellectual property rights that we have nowadays. Like, these are the entire fields that are around this, and these fields that have developed from what they weren't in the past and the development of the actual technology. And the question, did the technology spur this, or did societal changes change this, and what will it be in the actual future? So being a computer, just being a person who did calculations in the future, who did calculations, sorry, not in the future, but like now what is computing as a discipline has expanded with the technology as well. So before going into some of these history, what I want you to think of is some of the basic things you need to compute. And so this means like anything computing numbers, but also that information technology, and seeing what is required from this and how is this then embedded into the previous history of that, you know, like pre-mechanical, mechanical, electromechanical, and then fully electrical kind of computing, and how all of this is embedded within here and all kind of information technology systems. And step one is a way to encode information and seeing all of this. So how do I take information that I have and have data, and how do I encode this, turning it into another material or another physical device or signal or whatever we have in a physical world? So is this rockers on an adding machine, so literally pieces of material that rock back and forth? Is this voltage changes in electronic computers? Is this beads on an abacus? Even the picture here to the actual side where you're seeing, I can see times tables. I'm seeing 4 times by 5. Well, there's one example of like a pre-mechanical encoding of actual information. You have the number 4 and the number 5 and a time symbol, which really are just squiggles, but as a technology for language and encoding that within a physical material on something like these colored blocks, That is an encoding of information that then we have been trained that that specific shape means 4, that other shape means 5, that the 3, that you have certain symbols that then mean times, and we're trained that that is way, and that's encoded because I can say it. I can say that in language as a 4 times by 5, and then what does it mean to encode it in physical material? Then what does it mean to code it in voltages if we have representations of 1 zeros in electronic devices, which is key important, that you may not see, it's abstracted away from you, but it's key, that's part of that. And so through all these shifts in technology, you're going to see a shift in a change in materials that are used, our understanding and development of materials, and then our use of those materials in different ways to encode information and do work with it, which has a big impact on what can actually be done. And then even the theoretical side that's behind it, that most times people think, well, theory doesn't matter anymore, but then the history of everything we have theory plays a role as part of the societal thing to develop it. 2, beyond just encoding the information, we need a way to manipulate the encoded information. So is this gates or transistors in an electronic computer that we'll talk about later? Is this marbles in a wooden adder as it moves through the machine? Is this physically our understanding to actually change this from the symbols and manipulate actual language? So we need 1, that encoding. 2, a way to manipulate that encoded information. 3, a way to input and output the information. So nice to have. So a way to store information permanently. How do we get information into that material? How do we get it out of that material? How can we use something to actually process it? And what's all part of this? How do we see these things? And what are we used to for all of this? Because we're used to that with a computer nowadays, but how has this shifted through materials, social construction of material, technological determinism, whatever we're dealing with? Just how have we come to the point where we are today? So again, this is not a new idea. So the encoding, storage, computing, and decoding, so displaying information, has been done for generations. We're used to that. We just don't accept when we think the idea of information and technology, and information technology, that we seems to be perspective that this is more modern day, that we're increasing and progressing very quickly. But if you look back to history with these definitions, it has been done for a long time. Just how we're doing it, the speed at which we're doing it, and how it's being done, and what materials is different. And then how has society changed over time and evolved from that beginning points in time. So if we start way, way back and thinking of the pre-mechanical era, so this is before having a lot of mechanical devices being dominant and what played an actual role, there's a wide range of what you can see within technology. But if we look back to more information technology, so that encoding of information into a material, that manipulation of it and decoding of it, we can see something different. And as you see right here, this is a random tablet, and this is actually a Babylonian tablet with what's called cuneiform form, if I can pronounce that right. So Babylonian times and that need and requirement to actually store information. And that we understand today, we're used to that as we can see the symbols of 33 and how we write down numbers or how we write down everything else. But this need in earlier Babylonian kind of cultures to record information, that those taxes have to be paid, those animals have to be counted. We have to understand society, what we're doing in a way to record those materials another way. And this development of actually of actually keeping track of this information at a later time and transitioning in certain cultures away from an oral tradition into a recorded tradition of materials that then can be passed to people and preserved over time. And so one example here is Babylonians' numerals were written what's called cuneiform, so using a wedge tip reed stylus to make a mark on a soft clay tablet, which would be exposed to the sun and hardened to create a permanent record. And you have that first step of information technology of encoding it. So in materials of knowing soft clay that we know can be harder and can last longer, like soft clay or soft materials could be damaged in transportation, but once it's hardened, then it's easier to keep a form of what you're doing. And using something like a wedge tip reed, and that's why you see a lot of things within here that are actually these what looks like angles and quick things. These are things that quickly could be done by taking an angled cut reed and jabbing it in, which would create a specific shape to do a representation and understanding of what it is. And we need a way to understand that. And so this picture you're seeing to the actual right is saying 22. Well, this symbol here represents what we would call 22 in our understandings. And so we need to do this. And so you have that first encoding of it. You have a way to actually transmit it, that you can send it to other people. You can do computations and encoding of it is our understanding and then of interpreting the data ourselves as still part of the people. So we're still the computers ourselves, but we're encoding the information, we're encoding our memory into physical material that then can be sent to someone else, and then they should be able to understand because of that uniform way that has been written and taught that, okay, I can take someone else's stored thing and I can take it and I can process it. So we're still the computers as part of this, but now we're seeing a storage of the material, like of the information and data onto other materials that are then transferred to other people. You have the actual display of this as well because it's in a physical material. The memory can be physically seen and interpreted by us. So it is our input, it is our encoding, it is our decoding from there, and we are still the computers that are then processing that memory and that actual information. So here's just a small example also of something interesting about Babylonian culture and explaining things, and even where do we get stuff, and things like bases of numbers. Like where this video he's going to talk about base 60 from right here, but we're dealing with like base 10 numbers is what we're used to. So bases being when we write numbers down, how many digits do we have per individual space? And why was that done and material? And you can see what it means between the physical body playing a role within this and materials and the human still being that actual computer.
So the number we're talking about now is 60. Now, it's quite a big number, so you may not meet it all the time, but you do use it a lot when telling the time, because of course there are 60 seconds in a minute, 60 minutes in an hour. But why 60? Why this random number 60? Well, it all goes back to the Babylonians. Thank you, Babylonians. Because what they wanted back then is a very nice number that divides quite easily. So if you think about the number 60, what divides it cleanly? 1, of course, 2, 3, 4, 5, and 6. And in fact, it's the smallest number that's divisible by all of these. Well, why is this important? Because you can take half of it, you can take a quarter of it, you can take a fifth of it, you can take a third of it. You can divide 60 up in a lot of ways. So if you're cooking in this base, you can cook with lots of fractions of that. So if you don't want to cook a whole meal, you can cook half a meal or a third of a meal, or things like that. Again, if you're telling time, you can have quarter of an hour, you can have 20 minutes, you can have half an hour, you can have 3/4 of an hour. It all divides 60 very nicely. And when you don't have computers, you need a number that you can divide nicely, so you get nice round numbers at the end of it, so because they're easier to work with. So I mean, 60. Well, why? If 60 is so nice, why do we use 10?
You just asked my next question. Go on, tell me why.
Well, the idea is that we use 10 because we have 10 fingers, so you can just count along. As you're a child, you'd count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what's it's thought is that the Babylonians actually counted into 60 on 2 hands. They would use each knuckle on one hand to count to 12 and then count the number of 12s on the other. So you'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, one set of 12. And then you do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 sets of 12. And again until you get 5 sets of 12, which is 60. Highly divisible, and you can use it on your hands. So when the Babylonians were working with this number 60, they were also very good astronomers. And what they found is that the year is pretty much 360 days. So that's the length of time it takes for the Earth to go a full circle. And that's why the circle is divided up into 360 degrees. And further, each degree is then divided up into 60 minutes. You can have an arc minute, which is a 60th of a degree. And that further is then 60 seconds, 60 arc seconds of that 60 minute.
I wonder if we came close to living in a world where 60 became our base.
Like I say, it's very, very difficult. I mean, you could write, well, there's 57. We use it 2 numbers. For a Babylonian to write 57, they would have to write 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. It's a lot easier to write like that than that. So these are how they drew their numbers, because they had little stylus that they would hit into clay. And the stylus had a triangular end. So the stylus would look something like that. And so when they were doing ones, they'd use the tip and go 1, 2, 3, 4, 5, 6, 7, all the way up to 10. And a 10, they'd turn the stylus on the side and create one of those shapes. So each one of those is 10, each one of these is a 1. And so there we have 57.
Good. That's their version of a Sharpie. Yeah.
Exactly, yeah. But it's really good. 1, 2, 3, 4, 5, 6.
So there you have one example of that coding of information, but also how the physical body played a role, but also societal things. Like you mentioned there, like why do we have base 10 where we write like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 with the symbols we use now versus this cuneiform and base 60 way? Like why did one win over the other? And the fact that that is technology, and the fact that there probably is, to guess that societal choices and time and history and what was accepted may have played a role over all this. But we still have that information technology. But you see the key part of still the human being the computer, the physical body playing a role. Counting to base 10 because we have 10 fingers in general, versus looking at, well, base 60, a number that is easy to manipulate and communicate, do computations in our head, since we're the computer taking that memory once again, but also still having the physical body and thinking about a positional number system like we're used to with 5, 7 and being 57, and what does that mean? But just the fact of taking the fingers where you had 10, but just that the individual components of your actual finger playing a role of what could you count and what could you do as being that computer, playing a role of what we have as information technology earlier on, that storage, computation, what we have. And the fact that these still make it today, as we said, the base 60, the division of our understanding of what we call time now, of being a minute being 60 seconds, and like you have an hour being 60 minutes from right here, and that playing a role when you look at that representation on a clock and those division into components and breaking down time into certain chunks is what we're used to today, and that's still information technology, and how that has actually played a role overall. So that's that example of it, that we have earlier things of being this pre-mechanical, of having materials and storage and what we are, and us being the computers, but having a case where a lot of our memory and the encoding of it and the display of it was done through physical materials, and we are still the in-between the actual programs that are doing stuff. We are the computers that are making those choices. And so another example would be an abacus, which is used to perform arithmetic calculations. And it can do like adding, subtracting, multiplying, dividing, and it consists of a tablet or frame where bearing parallel wires or grooves in which counters or beads are moved in certain ways. And so it's a different way that people thought of encoding information and what it meant and certain actions and customs that were pulled out of it. And was it what was accessible for easy materials to use and make things out of and doing work? So we still have the idea of storage of information, the information technology, and doing computations in the beginning. Right now, it's still sticking toward a lot of mathematical, but again, when I say this of storage, it still means in other materials, and I'm just concentrating more on the mechanical side to deal with the computers, but we still can do more with that. And what does it mean for information technology? And so we still have in an abacus physical materials, it could be wood, it could be metal, that then represent the encoding of it, that then have to start to help the actual calculations, because compared to the cuneiform tablets from before in doing calculations, these are also then used as a tool to help doing calculations. And so combining with the human doing the actual calculations, it's doing work that helps that human to do stuff quicker and starting to get a little bit of the mechanical nature of computations where some of the work is done by the device itself, and the role of the human as the actual doing of the work, it's moved a little bit away. So if we step now from that Abacus into the realm of, and you can see why this is a fast, basic history of computers, we're going into the mechanical realm, where we're taking not just that encoding of information technology into physical materials, you're moving into that the encoding and the actual calculations themselves are starting to be done by the actual devices themselves, where you may get a human inputting it and the device allows for a certain way for it to be input, and then it allows for a certain way that it's output, and the computations themselves are done by the mechanical device. Now the reasons for it are still done by the human themselves, but we're starting to see a separation in these devices from the person doing all of the work to being a little bit more advanced tool, that the actual tool does a little bit more of the calculations, and then the human is still bringing everything together. And these are basic starting calculations that it does the work, and then the human does more overall synthesizing and bringing everything together for the overall work. And so this entire generation consists of mechanical machines that could do various functions. So they had moving pieces. And I'm not going through a ton of these. I'm going through a few examples to give you a feel that kind of lead up to stuff that we see from modern computers. But you can see in this physical device that's here, you see some of the fact that the encoding ends up actually being in the specific setting of gears and physical moving parts. You have the actual output signals as part of it is being done by the actual symbols we hear is that certain positions of things on tumblers and different things will show the output that you actually expect. And you have the actual calculations that are being done is by this interconnected machine that when one thing moves at a certain rate, it'll shift to other things at a certain rate. And it was figured out by people that this is the same rate to do these specific calculations. And so we have this encoding and presentation of information, some of the calculations being done now in devices, but this is all physical materials where different things are working together to do that actual work. And a lot of these ones in the beginning cases are just starting out to be some basic calculations that nowadays we may not see as valuable, but back in the day it was something that was done by computer people that could have had errors that were done like continuously by hands and required training. And what would it meant to have a device that then does this stuff for us and doesn't require people to know the calculations, just know how to use that device and does the work for them. It's a wide range of things that are used in different fields, and seeing this development of what also played a role within society for the drive for a need for something like this. What changed once it was there, and where are we now? So one example of even that device we saw before is the Pascaline. Pascal invented the Pascaline in 1642 for his father, who was a tax collector. Taxes and death again, so tax collector, and he had built 50 of these gear-driven one-function calculators which only performed addition. And Pascaline used a complicated arrangement of numbered wheels and that were connected by gears. So you're seeing the device here. You're seeing the internals of one of them and how it would be externally. And it seems really weird. Like, what would this matter nowadays just for doing addition? But if you're doing large-scale additions, and if this could do it faster. Now, more of these seem to be as a requirement internally in one area that this may have been useful. Someone who's just planning to make a device to do stuff, but we can see nowadays of how important these things are and what people view as the importance of technology and us doing it, of a human doing it versus having a machine do it. But you have a first mechanical device for that encoding, computation and change, and decoding and presentation of information. You have it between the setting of the actual gears and then the actual movement of once you set these, and you would get one simple addition out of this. Put it in, you get the addition out, and you can read and then use that number as to part into your tables on material books, whatever, for their tax collecting. So it's just one example. And it's not saying that this is our computers are coming directly from this one thing. There's a wide range of devices are out there, but in this era, you're seeing the development of devices like this. An example would be another one here is the Kirita Calculator, which is on the edge later on of being devices and where this came out of. And this is a handheld calculator. This is your calculator that could do a wide range of things that we would expect today that you could carry around. And as one example of development here, that was a highly complex device, but that could do a ton of different calculations if you know how to encode it by changing different physical levers to certain spots and twisting certain things which would change gears, and then moving something to cause the calculation and getting the number out. So we're still seeing here now a device where it's encoding it, and you have a way to see the results, and it does some of the computations, and then we as humans are still playing a role in the calculations of it, because we take those numbers and use it in some way and then reuse this, but we now have a physical mechanical device doing some of the actual work. And so I'll play this a little bit so you get to see a feel for this individual playing around with this device and seeing some of these calculations actually being done and how it sped up some of the actual work.
The item I'm going to show you today is one of the most precious things in my collection. A lot of people will know what this is already by looking at the name on the case there, but for the rest of you, let me get this out and demonstrate it to you now. This is the Curta Handheld Calculator. Let me give you a bit of background. I've always been fascinated in complicated mechanical devices, automata in particular. Like this amazing mechanical boy from the 1770s that's able to write on a piece of paper. And then of course there's the great story of the Mechanical Turk, which if you haven't read it is definitely worth a read. That's about a chess playing automata. It's probably the reason I've got a mechanical fruit machine in the house, just because I like the mechanisms on them. Now you can't be interested in all that stuff without being fascinated about Charles Babbage and his amazing mechanical computers. And the closest thing that I'll come to owning a difference engine is the Curta Handheld Calculator. This ruled the roost as far as portable calculators go between the late 40s and the early 70s before electronic devices took over. Let me demonstrate to you now how it works. So you put the numbers in using these sliders on the side. So I'm going to put in 1, 2, 3 on the side here just by moving those into position. You can see the numbers there now. Right, let's do a quick calculation. So we'll do one spin of the handle. That's 1 times 1, 2, 3. As you can see there on the top, it reads out 1, 2, 3. So 2 times 2, 4, 6. And we can spin it round 4 times to get 4 times 1, 2, 3 is 492. Reset that to 0 by spinning this ring around here. And now let's do a more complicated one. Rather than spinning the handle hundreds of times, let's just move it into the hundreds position. So now we could do 100 times 1, 2, 3. As you can see there, 12,300. So let's do 231 times 1, 2, 3. So we need another 100 spin. Move it into the next position. 3 spins in that one. So that's 230. 1 spin here brings up the result, 28,413. Much quicker than most people could do it in their heads. And if you spin it around, you can see on the silver side the digits that were entered to get that result, 231. And to reset it, you lift the top up and spin this ring around, and rather satisfyingly everything returns back to 0. I'll just do one more quick calculation to show you something. So I've put the digits in 4444. Spin it around, they appear on the top there. Now let's do a minus calculation. So we'll do a simple one. We'll just put 1111 on there. And to do a minus calculation, lift the handle up slightly, then spin it round, and it minuses that number from the other one. There you go, 3333. Now of course that's not all it does. It's a very complicated device. You can do multipliers, divides, square roots, cubes, factors, percentages if you know how to use it, and that's part of the fun, learning how to do those different calculations. I only found out about the existence of the Curta while searching for vintage calculators on eBay, but since then I've been able to do quite a bit of research into it because there's just so many website resources dedicated to it. As well as the usual Wikipedia article, you've got websites that really go into the Curta in massive detail, and there's just so many of them. You've got photos and videos. It's possibly one of the best documented things that I've ever seen. They've even got the original factory records which tell you when each Curta was made. On the bottom of each device you've got a serial number, put that into a website, and it'll tell you when your particular device was manufactured. And the one that I've got was made in August 1950. So how much does a Curta calculator cost? Well, if you look at this advert from, I believe, the early 1950s, back then it was $135 approximately. Convert that up to today's rates using inflation, that's about $1,000, which, believe it or not, is not dissimilar to the prices that they actually fetch on eBay. This is one of the few things that I've featured which has retained its value after all these years. So you might be better off just using one of the Kirita Calculator simulators that you can find online, and you can use those for free, and it gives you a bit of an idea how it operates. Now, whilst I didn't pay anything like those prices for mine, my Curta calculator is still one of my most treasured possessions, and I hope you've enjoyed having a look at it here today. But that's it for the moment.
So you see one example there of the mechanical device, but I also want to take one thing out of that historically there. He said that was 1950. Like the one that he had was developed in 1950. Like, if we think about that in times and what that was worth, and that this is something that's documented, and even nowadays people take a lot of accounts, but that device was being developed and sold and people were buying them, and this case of the need for computations doing it fast, that you had something that was encoding, you had to learn how to work with it, you got a lot out of it, and it could do calculations faster than we as people could do, and that replacement of people being the computer and the storage, but you're the storage and retrieval and doing work and doing faster in a mechanical device. But that's 1950. Like, on the day of this recording, it is June, my God, out of time, January 23rd, 2022. So that is roughly only like 70, I can do the math quickly in my own head, showing you that I don't have the Kirita calculator built into my own head, that's roughly like 72 years. Like, that is the age of maybe some people's grandparents now, or maybe not in that case. Like, we have to think in the context of time, what has that changed? And not jump too far into saying progress and change, but just saying like what we're using now and what we take for granted and what was computing wasn't even the same just 70-ish years ago in that timeline. And even your own age of what you expect being whatever age range you are from 20 to 50, whatever is in this actual course, if I'm estimating it, is that you're like, well, what does that computers mean for you, and what do you take for granted, and what's common sense to you in the decisions you make in society today, and our experiences and data and knowledge and what we know versus what was before. And you had these devices. You have this mechanical device. You have it that it was doing work for people. You have the encoding and storage and tracking of information, but still now done in that era in predominantly mechanical devices, and even before for a long period of time. But even when it was going beyond just a research for fun group area, that this is business, that these are being marketed and sold as products to general everyday public, and everyone having access potentially to buy these devices if there is actually a need for them.
As always.
So going back, and so Curta is way sooner. So we go back. We're going back in time. So we're going back to the 1800s and not sitting in the 1950s, but thinking of a different device that wasn't used to do calculations. Like, this is now information from a different case, which is a loom, which is fabric. Just an example of a machine encoding of information, but used to create fabric. So not just number calculations like we've been seeing before and getting too tied into that for information technology, but just the fact of storage and processing and what do we get out of this. And one example I want to bring up is the Jacquard's loom, and what does that mean for punch cards, and kind of showing an example of development of technology to where we're getting to our modern storage computers today, and that new definition of computers that we talked about of storage of programs that do stuff. And what does this mean? And we're seeing a picture of a smaller part of a Jacquard loom here to the right. It's only one part of it. This is the reader of it, and it may look weird, but hopefully over the next slides you get a feel for what you're seeing as an actual program to weave something and doing a complex repeated industrial production of materials. So in 1801, Joseph-Marie Jacquard, a French inventor, developed the Power Loom. So the Jacquard's loom worked by using wooden punch cards held together in a rope to program patterns in order to create woven fabric. The presence or absence of each hole in the card physically allowed a colored thread to pass or stop on the thread. So if you ever dealt the loom, there's usually a shuttle that goes back and forth that holds a thread that's then interweaving thread through other cords. And so different ways that you engage some of the threads will then create different patterns. And so what you are physically seeing when you see these cards you're seeing on this other side is we have a physical material that we are encoding instructions of how to do work. And then we're having a machine that then also then interprets that and then changes physical actions that are being done. So in this case, there's still a human component that's doing some of the work, so it's the design and encoding of it, but you're getting this program that then can be pre-programmed, and you have sequences, so they're roped together in a specific sequence that then can be made again and again and again to reproduce the same pattern. So one set of work to do something complex can be done then to create something simpler. And some of the people who are creating some of this work on the loom may not actually know how to do that weaving or doing that within their head. That would be the designer, which is someone separate. They could just know how to operate the Jacquard loom. And so the training of individuals to do this work now shifts. Some are trained to develop the actual weaving and programs. Some are developed to actually maintain the actual devices, and some just using the devices. But then that you can load and do these pre-runs and the changing of even what it means to educate what people have to do for work and what you are getting out of these actual devices. And so this is a precursor and development of ideas of what we would see for modern day computers. So an example here, maybe hard to see because I just blew this up, is an example of one of these punch cards, which makes no sense to us. Like we need something else that's going to interpret this unless you know you've been trained in this encoding. So we have a physical material and you have holes that are within it, and you can see that everything lines up. You have holes here that are then to pull the program and step it forward from instruction to instruction. And each one of these slats is one set of instructions for the way the thread should be moved. That should be opened up to create so you can have an actual pattern. So you have sequences of instructions. You have ways that it's pulled forwards, one instruction after the other after the other. You have a case where physical material will go through these holes, which will change some other component of the machine to result in what it's doing. But it's still mechanical and not electronic at this time. It's fully mechanical, that by pins falling through these holes, it'll shift something else within the device, which will shift some of its work, and then you can lock in one instruction, have one thread to go through from a pattern, and then you go to the next and the next. And so we have the idea of a program here, a set of instructions. And the only way things that repeat is by having you create and you program it into that material of that slat. And then you have the next and the next and the next and the next for the entire program. And by the end, if it's not repeating, you'll get some kind of pattern. So either it loops back around, starts repeating the same pattern. So by the end of one loop, it finishes one part of the pattern, then repeats the next and repeats the next. And you can make it end at some time or continuously keep producing whole reams of the same material. And the skill sets of who does the work start shifting. It's in the machine, but we start having specialized jobs to create certain things like these programs, to other people to use the devices to maintain it, and the shift of what can actually be done. And so you see another example of the programs here. You see these lines that are coming through here, which is actually the woven fabric that's being lifted up, that then a shuttle goes back and forth for the actual loom itself. And to make this easier, I have this video here. You can watch the actual person using it.
This is a mechanical Jacquard loom. This technology was developed in France in 1803 by a weaver named Joseph-Marie Jacquard. The key thing about this loom is that it controls every warp thread, the threads that go from the front to the back of the loom, individually. Because it can do that, the loom can create very complex, fancy patterns in the cloth more quickly and with greater accuracy than the technology available before this loom was developed. These cards are what carry the instructions that are read by the apparatus on the second floor that tells the loom what pattern to create. The holes in the cards are read by a series of pins up in the apparatus, and those holes tell the apparatus which threads down here should be raised for each pass of my shuttle across the warp. Some of you might recognize these cards as looking similar to computer punch cards. Back in the early days of computer technology, punch cards carried instructions that told the early computers what kind of calculations to do. So this loom is the great-great-great-grandfather of the computer technology that we all use today, and that technology started with a machine that produces cloth.
So you see there that first step of that encoding. But the first off that, this is something that can do really complex patterns where the skill doesn't always have to be with the person who's using the loom. They're just sending that shuttle through the threads back and forth every time, maybe like loading different certain colors of thread and making that decision. But the actual pattern itself is just step next, step next, step next, step next. And that's encoded into those physical cards. And you're seeing this idea where we're shifting the idea of the earlier being a computer being part of it and the human playing a role to a computer that we see nowadays of that stored machine and program that's manipulating it, and that's in those cards. And this is still in that mechanical era that those cards have the encoding that then does work for us, that you can now reproduce this same complex pattern. It'll take a special skill set because someone's got to make those cards in the beginning, so they have to learn how does that encoding work. They have to know how to abstract from the idea from the physical pattern to the loom to this from here, and the idea of early programmers that have this development, and that loom itself acting like a computer of storing one instruction, executing it, then the next, and the next, and the next. And you're having that encoding and then the decoding, and we're getting fabric out of this as this output for this information technology in this mechanical realm. And you'll see similar things, and why they say this is earlier generations, of what does it mean for this converging of physical, mechanical, electronic, and other things are happening in society with the theories, and what it means that we can do computations, and what can it mean for solving just any problem and doing any work for us. Because be aware, underlying everything we're doing for all these graphics are electronic signals and instructions and calculations and numbers that are then translated and encoded and decoded through different materials to create what we have now, and what we view and take for common again to be common sense, even common sense for the jobs. Because doing those loom work before is that you had to be a master craft of the tool and everything and the pattern, and you were coding and making and everything, whereas now you have an abstraction, a separation of who does what task that combines what you see and the time when that task is done. That programmer is not there with that person at the loom at the time who's using it. And they could be the programmer themselves, or they could be someone else who's just using it and is not aware of what do those cards mean at all. They just know follow these instructions to get this to actually happen. So next we step into not just mechanical, but taking steps towards mechanical to electronic, a shift in devices, a shift in what we're using. So things that weren't just purely mechanical moving devices, but now this new development and understanding that over time has developed to controlling electronic signals, something, a material in a lower sense, like this circuit board and this resistor for people who recognize in a breadboard if you have any background in wires. And what does it mean for all these materials? Because we have all these other materials, but what does it mean now when we're working on a different realm of not physical connections, but the idea of electronics and the development as society's changed and understood and grown and learned new things over time, and what's become dominant from right here. And so the same thing for these devices, how has this shifted and come closer to where we are now? So you have to realize that there's a lot of other things that have started to play a role to where we're getting. And I'm really simplifying this down. It's only been about an hour that we've been going through this history, and we've covered a lot. So there's way more that's going on within society and development, economically, politically, like on multiple different levels, and socially what's been changing and what are driving to, and even theoretically within the science research world and universities and everything else, of what's been being developed. And you had that dominance of being mechanical devices, but also now this emerging world of electricity and the understanding of materials as this was being discovered, and then how can this be harnessed, and even the economical and business world realm of gaining these materials and having access to them and mass production. And one thing that started playing a role, if we're looking into the idea of modern day computers and still that information technology of encoding and decoding and having to have some way, is the idea of like a switch. And the first beginning levels of this for like electronic switches were vacuum tubes. So initially discovered by Thomas Edison, the vacuum tube formed the building blocks for the entire electronics industry that we have nowadays. And vacuum tubes were later used as electronic valves in the 20th century to build the first electronic computers for having on and off, which is going to be this leading point of encoding, where we're so used to stereotypically seeing ones and zeros when it comes to computers nowadays, but that's your encoding of information and signals of on and off. No light, there is light. I'm not saying this is what vacuum tubes are giving light, but this idea symbolically of electrons flowing through an actual wire, of there being current or no current, and what can be read, and what does that mean for encoding, decoding, doing work, and the manipulation of information by a machine, and being done faster in these machines than we as humans playing that role of computer, and more of that shift away from human as the computer and then human-machine interaction to still having human-machine, but the machine doing more and doing it faster and doing it more complex, and the user sometimes needing less and less understanding of the physical materials and the encoding and what's being done underneath all of this. So again, lots of stuff from here, and just saying like with the vacuum tube is that there are physical properties and things that are changing in devices and sizes that are allowing for the development of something different. And you have these developed machines and people being inspired and innovating and changing stuff from here, but a need also coming out of this. Which we get into the question of like, is need the thing that drives it, or were there other factors? But looking at another example that had a big impact was like Hollerath's tabulating machine. And this related back to the importance of governments and censuses, and this is in the United States, and how long it took for physical recording of these to then more of like, well, using machines and things to do this, and getting from mechanical to electromechanical devices. And so example, the tabulating machine is that every decade the U.S. mandated a complete census of its citizens to be able to make decisions using data and the importance of data as a driving force within society and government at that time. And the 1880 census took 8 years to complete. Like, think about that. To do the census, it didn't get the final results for 8 years after that. So 1888 to understand the 80s. And what's changed in 8 years within that society. And so the accuracy of that information and what could be done with it was difficult. And the amount that had to be dealt with. And so the population between those times doubled. So from 1880 to 1890, which led to inaccurate figures. So just the time it took to physically do that and requirements, and a quicker method was needed. And there was stuff that was put out for here, and one thing that won out. And so like the U.S. Census Bureau set up a competition that was then won by Herman Hollerath. I doubt I'm saying that name properly. Again, apologize. But Herman Hollerath invented a calculating machine that used electricity as part of it. So still had some mechanical components of it, but electricity played a role. And you're going to see it's going to be similar, what seems to be inspired, if we don't know what came from out of that realm, but the idea that we saw in that Jacquard loom. So he used the same idea as in the Jacquard loom. I don't know if he was myself personally respected by this, but like, is that the machine personally inspired by Jacquard, specifically other technology that was developing because of ideas around it. But the machine consisted of a card reader which sensed the holes in the card, and a gear-driven mechanism which could count using Pascal's mechanism, and a large wall of dials indicating the display of the results that were counted. So the idea is that where the holes were that you had in the device is that metal went through which could complete a circuit, and then where there weren't holes, it wouldn't complete a circuit, and that would trigger different mechanical parts to shift, which is a counter. And so you're seeing the idea of someone who's inputting them here is that they have the card. So someone else, when they're recording and doing the census in remote areas, would be encoding the information into the actual cards themselves. The cards then are sent all to these actual machines, which then do the actual tallying up of it. And you can see each of these dials here would be a different thing that it's tallying up. And the idea is that when you put the card in, and you can see the person operating it right here, is they would bring it down, completing the actual circuit, and certain wires would make connection which would allow electricity to flow, which would trigger certain components to actually click up once as part of that. And you can see these other people and different people who started taking on these roles and jobs that were part of this. The people who did the work of actually having specialty machines to do the actual punching of the information and census collecting, and what that opened up for skill sets for people to do for actual work. And then sending to others. So again, the separation and coding of information, that we have this information technology that's driving and having this machine. And here's an example of one of the actual cards themselves. Is that different encoding between here to different parts of what they were trying to tallying, and when they were taking this one card was an encoding of one person's information within there that they then tabulate up. And the idea is then the machine could take this, and these little holes here, that's when a wire would complete and then would allow for quick calculation of the tabulations. And so this could be done faster through this combination of physical encoding material to electrical mechanical computations that still involve the human as part of it, but the actual tallying calculation was done by the machine, and the rest of the operation and encoding was done by someone else. And the fact that you then had the output that we're seeing here screen. So, oh, that's fast calculator. So Hollerath's tabulating machine invention was used in the 1890 U.S. Census, and Hollerath's machine was immediately successful. The general count of the population, then 63 million, took only 6 weeks to calculate, whereas when it was even smaller population before that, that took 8 years to calculate from right here, and that's huge. And he developed the Hollerath Tabulating Machine Company out of this, which was later changed in 1924. So you can see it. This is from 1890s as a company to 1924. It became then International Business Machine, so IBM, which we may not see as much today, but it is a big competitor in this field of what we have for modern day machines. And these earlier ideas of electrical and mechanical machines and people playing a role, and the shift of jobs and the need and more information, that encoding and exchange of what actually happens. Now, going even further forwards, there's a lot of other things that have happened, but bringing in like a bigger thing of like, well, what did World War II, what effect did it have on this? And again, this is a brief history. We're an hour into this. There's way more that you can go and research behind this, but I'm just trying to lead up into what we're having now, this era between that pre-mechanical to mechanical, and now we're sitting in kind of electrical mechanical kind of world of devices that are being used. And in the 1940s, the need for calculations outstripped the supply of human calculators. So this was still here. Like, it wasn't like these machines were doing away with people who were doing calculations and who were computers and who were the calculators. Is you had these machines that were roles that were used by these people or people who were still doing it, but then the demand and need for calculations in this case outstripped it. So there was a different push for what was actually needed in this case, and this belief in this technology. So in World War II, things that were needed, like artillery firing tables, signals of encrypting and decrypting of information, the Manhattan Project, anything around that, that's the development of the atomic bomb, new scientific weaponry at this time. And I'm not saying these are all the driving force and the only thing that was going on at this time. This is just one example of things that pushed and shifted what actually happened and why the technology was there. And so the massive calculations needed for decrypting during the war motivated the creation of the first computers. Something that could do it faster, where the computers are doing more of the work, but we still have that encoding and execution and having programs that run and do some of the actual work, and that are needed for a wide range of cases for how they're actually used. And this is still 1938. We're still within that 80-year range, roughly, from this. 80 to 90 years at that in human history from this development of then to now. And there's other things, example, World War II, the German Navy developed a cipher machine named the Enigma. And the Enigma machine could automatically encode a message in such a way that only another Enigma machine could read it and decode it. So you have these electrical mechanical machines. You would look like a typewriter, and you have these gears that you see at the back that could be organized in different ways, and they still had electric signals, so someone could encode it by just typing it like a typewriter in a machine, where you understand the keys and the symbols and getting used to that. What we see as kind of keyboards, you pressing a key which then sends a signal, and then it goes through this cipher here, which then filters where it actually is, and encodes it to being a different character on the other end. And then only another machine on the other side that's configured the exact same way could put in the character and reverse those steps to get the actual output. And so the need now to even protect information that's encoded and information needing to be transmitted over locations, and the importance of information to make decisions, that if these are then being used by one side, the other side trying to take it and have a way that you can fastly try to break those potentially. Now be aware, I'm not saying there's machines that played a whole role there. Again, there's more history, but this is the role of the machines and information technology and this shifting of people and who are part of this. And so one person that played an important role as part of this, like played a role within it, but also in the idea of modern field of what is the computer discipline and what it is at all, was Alan Turing. So Alan Turing was a British pioneer computer scientist, you could see. The term didn't really exist back then, but being more mathematician, logician, cryptanalysis, and theoretical biologist. And he was highly influential in the development of computer science, the field that we understand nowadays. So the people who are in computer science and the theory courses, you're going to feel like the effects of part of what he was part of that directly. And you also have people in other fields that you may not realize it, but this was impacted by him. And he provided the formalization of the concepts of what an algorithm is, so being a program, and computation within the idea of what is a Turing machine, which seems weird, but the modern day of what we just take for granted for a machine that can solve any problem that we kind of throw at it, and we have programmers that can develop to deal around it. But that theory that didn't even exist society as a thought before then, the theoretical realm of proving that, and the physical implementation of bringing that out. And so Turing was widely considered to be the father of theoretical computer science and even the idea of artificial intelligence, of what we see, and this is in earlier days. And during the Second World War, Turing worked for the government code and cipher school, and this is in Bletchley Park, and this is in England. And Turing played a pivotal role in cracking intercepted coded messages that enabled the Allies to defeat the Nazis in many crucial engagements. So he's not the only role. There's a wide range of what's out there, but now we're seeing the impact that technology and information technology is having even with the idea of wars, and people playing a role that may not be directly on the war front, but they can take things and impact things back and forth. And what did that mean? And this is, historians can go further into this for wider impacts, but we also see this burgeoning growth of even the field of what will be in the future called computer science and computer disciplines, and how that shifted over time. Now, one thing to always remember is society things behind the scenes that play a role, and where people could have been, and what dominates things that could change what technology came out of this. And I just bring this up not more as my computer side, but the fact that there's a humans behind this, is that behind the machines we see now is a history and culture and people that played a role from multiple different cultures to get here, of the materials, culturally acceptance, marketing, economics, but people were also affected. And this is just a history thing that, like, I also think was quite disgusting at the time, is that, like, Turing was prosecuted in 1952 for being homosexual. That at this time that this was illegal in England at this time, which such behavior was a criminal act in the UK, and that's just 1952. So again, we're in 2022, so you're looking at 70 years time, and that was illegal. And he was accepted for treatment, because this was wrong, with injection, so chemical castration, as an alternative to prison because he was homosexual. And he died in 1954, 16 days before his 42nd birthday, from cyanide poisoning, where he killed himself, where these kind of things could have played a role. I don't know more of the history. An inquest determined by his death and suicide, but it has been noted that known evidence is equally consistent with accidental poisoning. So it's not known if this was accidental for other cases or what came into this, but still, this is a history of the people behind this that we benefit from their knowledge culturally now, but then society didn't give a shit about them then. So either way, history. So the other thing I mentioned is Alan and the Turing machine, and this is a theoretical thing, and people who are taking computer science and doing theoretical courses from there, this will play a big role. Like, back at this time, it was like a Turing machine, and other people played a role, the idea of these machines, but like a Turing machine is a theoretical computing machine invented by Alan Turing, so 1937, to serve as an idealized model for mathematical calculations. So you have the encoding, manipulation, and input and output of information. And so this didn't start as the idea of physical thing. It's just the idea of what could we have if we have encoded, messages, if it was these one long tapes and a machine that could move back and forth, that could read and could write and could change and interpret the information that was happening here, and showing that you could start taking anything that can be calculated by a person, or calculations could be also then done by a machine itself, and the fact of encoding it within materials. This diagram here you got to know nothing about, but some of you that are in computer science may start recognizing that as the Turing machines. Usually when you go through computer science, it's something you have to deal with, or seeing those. But Turing machines were one of the first, if not the first, theoretical models for what we have for modern day computers, of sequential states and executing instructions that then represented an algorithm that from point A to point B, it will try to solve a problem. And the fact that we could do this in this weird different encoding, had to learn to do some of this work. So Turing's work was transformative. It made it clear to designers of early electronic computers that calculating machines didn't need a huge inventory of fancy instructions or operations. All they needed were a few registers that were always available, so could access this and be the state of mind of memory that's used, and a memory store that could hold both data and code. And the designers could proceed in the mathematical certainty that the machines they were building could be capable of solving any problem the human could program. And this is a huge thing. You may not see this. People who've done stuff, like if you're in BCAS and you're doing the Architecture and Operating System course, you're going to see that idea of registers and information and your instructions, and the idea of stored programs and what does this mean. But this is the basis of our modern day CPU, our central processing unit, what we think of as the brain of our modern electronic computers. And they have the idea of what's called registers that store pieces of information. You then have memory like your hard drives, USB, solid state, whatever, that stores the actual encoded information for your entire program, and only certain things need to be loaded into the CPU at certain times to actually execute. And you can switch this back and forth. That you're starting to lead towards general purpose computational machines that aren't just designed for one adding or tabulating of census, but you are starting to actually get the theoretical proof that you could do anything using this style, and changing up what could actually be done with machines, what could be done electronically and mechanically, and the design of where we are now. And so these insights provided the mathematical formulation for today's digital computers. Though it was actually the John von Neumann architecture that I'll talk about a little bit later, who took up Turing's ideas and is credited with the machine's design, so the actual physical. But that beginning theoretical thing played a role, showing that this could actually be done, and inspiring other people then to design things around that. And you get things like John von Neumann that started designing these things of what we have for modern day computers that we take for granted, that it starts doing this work, that we as humans are using this and have this import that we could ignore and say this means nothing to us, except it affects in everything that we're doing, even this video and doing this work, and jobs and future parts of industry, and the impact that it will actually have. So John von Neumann, von Neumann's design had a central core of memory that you think of what is physical material where stuff is actually stored, that fetched both instructions and data from memory, performed mathematical operations, stored the results back into memory, and then repeated these actions. And the machine could also query the contents of multiple locations in memory as necessary. What we now call the von Neumann architecture is at the heart of every microprocessor and mainframe and computer on this entire planet. It is dramatically more efficient than the A machine, but mathematically it's the same. So these are like other architectures that are out here in the development, and even this idea of what we have for computers coming out of this that we take for granted, but that computer scientists, engineers, and other people on a lower level actually build. Like that's where we are today, is this idea first beginning with John von Neumann and Alan Turing, and other people that would play a role that I don't have a background history in, but as being society. And here's a visual representation of this. We still have, once again, our information technology, what we've had from pre-mechanical to electrical mechanical, where we're getting more into electrical after this, as of having some kind of input device that we are now getting, and then having a central unit that can then store these instructions and do calculations and look stuff up and keep track of things in memory within it, and then outputting it. And this basic idea that we see here is the basis of everything we have today for like computers as we know it. So going more into the electrical mechanical world and getting even larger scale, we have first examples which are huge machines that seem like, why do we have these? And we're still having large institutions and not as much public in these cases, but the use of them is things like they have names. Like this is the Mark I. And it was built by a team from IBM. So we already learned about IBM earlier, and the Harvard University. And Mark I used mechanical telephone switches, which this is the earlier days of other forms of technology, communication, and telephone switching to make connections between people and communicate this, which had electrical mechanical components and switches to store information. And it accepted data on punch cards and processed it and then outputted the new data. So you're seeing now actually that same thing of having memory, like the von Neumann architecture of storing it, doing calculations using electricity. You have the inputting on these actual cards and programming, and you're getting the output and doing it faster, where humans are still part of this, but are now becoming the programmers to put stuff in and the developers and maintainers of the machine. But the machine is doing calculations faster than we can actually do and doing work for us. And after this, and looking at this in 1946, so again, 1946, within an 80-year range from then to now, I'm going to do the math right on that. So roughly 80. So that's roughly definitely under 90, but definitely like 80 years. Think of 80 years. You're going from this machine being ENIAC, where these are huge entire room machines that are government military kind of products from right here. And so the ENIAC was the first US-built all-electronic computer, so not mechanical, using all electronical components, and this is where that vacuum tube comes into actually play. There's no mechanical moving parts, it's all electronic signals that are going through all of this, and it was being developed to try to perform ballistic calculations faster. And this was not done with IBM, who was the dominant company of everything at that time for the idea of computers. And this is starting to be other industries coming out of this and other developers from this and stepping away from the electrical mechanical to the fully electrical machines. And now the equivalent of what's done in this entire room can now be done on calculators that you can buy at a dollar store that we expect or you can get cheap, but that's within an 80-year time range of what we're working with and what allowed. And so here you see this entire actually set up machine of the chaos with the programmers and what that took between setting up the ENIAC machine. You have physical wires of different length that have to be connected and putting everything together in the maintenance of this, but it could still do calculators. And we have that human information encoding and everything else component, but the human still playing a role, but a machine playing a bigger role and us interacting together. So it was 1,000 times faster than Mark I, but it drew a lot of power that dimmed the lights of all of Philadelphia, where it's being developed, when it was switched on due to the use of vacuum tubes that had a lot of heat and a lot of energy. But the thing is, the speed it was just. So the Mark I as a machine could do 5 additions per second, whereas the ENIAC could do 5,000 additions per second. And the ENIAC was made of 18,000 vacuum tubes. But at this time, that seems so small. We're getting into gigahertz and later on we do for instructions, but you have to think of how fast could a computer that was a human do it versus this now, and the shift and dominance of it, and why even culturally the term computer has shifted away from being a person who does it to a machine that we do it. But that development within society and everything else is encoded explicitly and implicitly into the machine that we have nowadays, of societal things that then happen to physical materials and economics and marketing and everything that came out of this and decision to get to the point where we are now. So, but the problem with ENIAC tubes is the short life of vacuum tubes, that they would die and need to be replaced. It runs a single program, which means rewiring by a group of technicians is needed to change for a new program. So you could do it, but you needed a group of people to do an entire program working together to physically change it to load a new one. And a solution is the same group of researchers worked on another version of ENIAC that could store programs on punch cards that are much easier to manage, and they came up with the next one of the electromechanical, so the Edvac machine. So you're seeing this develop and the shift, and this is the 1951, that the encoding and storage of everything is now not just between physical things that we are actually doing, but going towards actually electronic storage of the programs and change of what's being done. And so that was the Edvac, so electronic discrete variable automatic computer, but it was never completed. Instead, as another machine that came out was the Univac, so Universal Automatic Calculator. And 40 of these computers were sold to businesses. So General Electric was the first company to acquire Univac. And the first Univacs were used in the U.S. Army, Air Force, Navy, and Atomic Energy Commission. And it's also the example of the first commercial computers, so not still in public and in homes, but in 1951, and getting this era now of, and you can see this is overlapping with those mechanical devices that were still being developed, like in that Curta, that they were still mechanical calculators that were being developed, but making it into also public access and being used. But now we're starting to get is that commercial uses of these and large scale uses of these is starting to begin. Like, 40 is a small number when you think computers, but at that time, the fact that there was even a desire for 40 of these larger machines to do work. And coming out of this, and a shift from the business research kind of world and later on in future into public sector. And what does that mean once different people get access to it? But still now we're getting into electrical, mechanical, and electrical machines. And so as part of this is that von Neumann architecture played a big role, especially the Edvac. And this describes a design of architecture for an electronical digital computer with parts consisting of. And so we're getting this design of this, but now a computer's having these physical parts, like a processing unit containing an arithmetic logic unit and processing registers to store it. And that's our CPU, and that came out of the actual, the theoretical, Turing machines and other work that was done earlier on, is that theoretically done to physically, and that's our CPUs. A control unit containing an instruction register and program counter, and that's still part of the CPU as part of it. A memory to store both data and the instructions, so not just information, but the instructions for the programs themselves. And external mass storage and input and output mechanisms. And this is everything that we see, our keyboards and everything that we're used to nowadays. So introduce the idea of stored program computer. A stored program computer is one which stores programs and instructions in electronic memory rather than external sources like punch cards. And that's just a given nowadays. Like, we're in the generation where, even for myself or younger, that's not something I experienced at all with any computers, but the generation before me did. And then your generation, no, there's different ways that we're dealing with them, what we expect nowadays versus what we're viewing locally. And we're getting into the idea of the actual electronic side now switching away from being less of the mechanical devices and now going towards more of the electronic. And this is more things converging together. And realize I'm doing a simplified version of this history, but you're still now looking at developing things that have gone with business culturally and as we've changed over time to bring in different materials and things that are then converging for technology between different choices. And so if we now start stepping into more of the electronic realm where we don't have mechanical electronical mix but getting more purely electronic devices, there's two things that we have to present that played a big role in computers and technology and things that we're dealing with today, that why we so start viewing technology as being this science, mathematical, physical kind of material things, and that development of electronical devices. And the first really big one was the transistor, which most people may not give a crap about. But the transistor in 1946, that's overlapping, and we're a lot larger, and there's pictures of transistors next here, and they're all different sizes and developed from here. But it was very important in this transitioning away from these large vacuum tubes for switches that were needed for the encoding, decoding, and changing of information, and getting into the transistor. And it's the most significant single invention of the modern era, and it was invented by three scientists, AT&T's Bell Labs. And transistors are small, sometimes microscopic devices. They're microscopic compared to vacuum tubes, and they deal with they're fast and don't need to warm up. And they deal with that switching on and off in ones and zeros that we need for modern electronic computers. And so this development of the idea of transistors started shifting things of what we expect today and everything that's built into it that you may not be aware of it, but plays a huge role in what we do. And the transistor allowed for electronic devices to go from these light bulbs that were really large, taking up entire rooms that represented a 0 or a 1, to these little transistors. So it became a point of where, with this development, you started getting smaller devices could be developed. And then what smaller devices then allowed. And so these smaller devices then became more portable. And the evolution of tech from vacuums to transistors and cheaply developing this and size, and then what size became when designers and different people started using and what that started allowing to what we have today. And so each transistor acts as a switch. As the transistors are turned on and off, current either flows or stops. And today's transistors can turn themselves on or off 300 billion times per second. So the rate at which information can be flowed through here, your encoding of changing the information we have now into ones and zeros and can be put through the system, is being dramatically faster than it was before, and allowed for the shrinking size of these as more development came out of it. So its importance in today's society also rests on its ability to be mass-produced using a highly automated process. So semiconductor device fabrication that achieves astonishingly low per transistor costs. And so even business and cost and development playing a role within these and what it meant. And then if these are easier to make, then developing devices out of this that then use them, and who can have access and what can be done with it starts shifting. So transistors themselves in this development over time paved the way for smaller and cheaper radios, calculators, and computers and other devices. So even the cost of manufacturing and the access and the size and what can be done and who's doing what with what starts shifting and playing a huge role. Now the other thing that played a big thing is the chips, like computer chips, as we hear about. And then what does that term mean nowadays? And so ICs are being integrated circuits. And the IC revolutionized the entire electronic technology. So the idea here is even this picture you see on the other side is earlier things here. This is an entire circuit in one thing. So instead of having these large circuits and putting everything together, you had this smaller self-contained device that did everything, that the pathways, the transistors, and every other component was on this tiny little device. And what that allowed then was mass production of these units that then could be connected to other units and sold in these integrated chips. And you're seeing like a really earlier version here in the actual picture, where this is one medium that everything's on, and you have these pathways of conductor areas and things that are then within it, and it's self-contained, that then these points you're seeing this other side for allow for other connections, so this can be manufactured, and then people can use this as a component to develop their devices, knowing that this internal little device does something. And here's other pictures you're used to seeing these. If you're looking at devices, the integrated thing is that these are little things that have contained material that have entire circuits that do certain work. They're then built into it. And so our processors, our entire components of things are then contained within this. And then these can be mass produced and then used within devices beyond this. And so, and this shrinking idea, and that these contain the transistors and contain everything. And so these can be developed, and other people take these, develop other things on top to build our complex machines that we see nowadays, and everything from this in the electrical world that we're developing into. And so if we're looking at this now, stepping into the 1960s already, you're getting a huge growth in computers. So political, like the Cold War, the space race, other things, the way they're being used in society, economics of everything that's developing after post-World War II explosion, social growth of the baby boom, technical reliability and cost of that it's more reliable, the cost is coming down, people having access to it, a belief in progress and technology playing a role, with a key part of that tying into sciences and getting to where we are nowadays of what a computer is, and this huge shift from it being less about a computer being a person to being people using these tools that we then use to interact in between, and these taking over. And the economics of development, the size and scale, and who has access to it nowadays, of not being the upper class. Looking at everything else from personal computing, of every machine that we just take for granted nowadays, and that timeline of what you actually had, and the development of other things in the development beyond just the John von Neumann architecture, but physical architecture and what was done for these machines to get it into people's homes. Looking back, 1976, earlier Apple computers with like Steve Jobs and everyone else of the Apple I, the development of the floppy disk and what that was, that most people don't even know what that is now any days, to the idea of the hard drive or hard disk just from the 1980s, to the development then of even the ideas of then operating systems, of having a stored machine for computer, but then a program on a machine that manages a whole bunch of other programs. And what is that? And the idea of MS-DOS and Microsoft and everyone else that's developing this behind the scenes, and other history that's played a role if you look beyond this. But if we look at this timeline, this is why, and like you're starting this development, this is why we're saying like new things that are coming out of this, integrated chips, your transistors, everything else, medium and materials, and then what we actually expect for storage. But think about that. Like, think about this timeline. Like, I think personally, when I see this from 1980, is like I was born in 1981 and I'm 40 years old right now. And so this is the development of the hard drive and MS-DOS. This is around when I was born. And even as a kid, this was not something that I saw going, even making into schools and where I lived in Saskatchewan, like before this, that like no, I didn't see any of this. And it wasn't even until later on into like, I think junior high school, that computers in a school were a thing at all, that you would occasionally have a computer class. And what does that mean for a field, an industry? And think about these industries and the job, and even the school field. People who are in computer science now and in BCIS, this didn't exist before. And this new change within society, what we have is development and the drive of what's needed and what we have for jobs and what's actually expected in that timeline of where we're at. Which is, as I talk more excited, maybe think that we're progressing a lot here. But again, that's a progress view, but there's still a lot of society things that are behind this. So look, going in 1970s, so taking a step back from this, is like my computers and home computers. You have the Atari 8080, the Apple I, the Apple II. Starting out, this is the beginning ideas of the internet, not as we know it now, but the idea of the internet being a university and military application to connect telecommunication industries that were also going electronic more at this time, to combine with electronic computers and what is even networking. So beyond computers, but having computers connected together and exchanging information over long periods of time, and that development and having that free access when we have these networks that are put in place that people used for telecommunication first, but now are going to be used in other ways, and the development of what we see as the modern day internet and what we have now versus what it was. And even the idea is Moore's law of like this continual shrinking and changing of size of technology and affordability, and then the power of that technology and what it could do. So with Moore's law, it's just the observation that the number of transistors in a dense integrated circuit doubles approximately every 2 years. So based on development and what they're able to do. And this means that electronics have become more powerful in the calculations that they can do. And digital electronics have contributed to world economics growth in the late 20th century and early 21st century, and why a lot of people see as that dominance of what drives us and what we go towards and what's important to invest in, and opening up whole new fields that never existed before, at least by some perspectives. Or is it just a shift? And Moore's law describes a driving force for technological and social change. That as we go from these earlier times of what we're seeing of like Hollerath's tabulating machine for how many computations could be done, and IBM's machine, to Colossus, to the Univac and ENIAC machines, to modern like what we're getting for current day calculations right here, to what we're expecting nowadays more in the 2020s and projected beyond, where we have, you know, the iCore 7s and processors and the speed of what we're getting. And so seeing that earlier era of electromechanical to solid state machines to vacuum tubes, getting so transitioning to more of the electronic side, to the introduction of actual transistors themselves, and then incorporation with the realm of after just transistors of having integrated circuits, and these development of where we're going in that developmental increases, like this just mapping out of the actual numbers of executions that can be done per second, like so calculations per second per $1,000, what it could actually do from right here in this time. And so what does that mean versus like what we can do versus the brain and other stuff, and will that go over? Like, will things change? Like the future of quantum computing and stuff like that, what will the future bring? And will that Moore's law progression keep going? And is this the same trajectory that with our technology we are also going at this exponential growth of change? And is it the technology driving it, or is it us? And it's questions we're going to be coming up to later on in the actual future. So beginning here, but is this what's happening? And so even going now into like, what is the internet? So going to the 1990s, which for you is like ancient history for a lot of other people. But for me, this like, I was born in 81, so I'm like 10 in the 90s. I am 10 to going like into the late 2000s. But you think 1990s to earlier on to early 80s, like late 80s to early 90s is the internet. And what that is going from a military application and university into a public domain of what we see it today. And then not just the internet, but being the World Wide Web and what it is. And again, that is only like, that's in a 40-year period. Like, again, put that into context for your life of how much you depend upon the internet, what we do now. And that's 40 years to where we are today and what we're using it, and even how I'm teaching this course. And so this is why I want to pull up here a Canadian Triviana. I'm bringing up like an old CBC news thing that's just in 1993 talking about the internet itself.
There's a revolution going on in rec rooms, offices, and classrooms around the world. A revolution in which 15 million people are taking part. They're sharing scientific data, arguing philosophy, or passing on cooking tips and gossip night and day through a computer network called Internet. For about $200 a year, they log on to personal computers connected to phone lines and communicate across cultures and continents. Bill Cameron has this report on the growing phenomenon of Internet.
The electronic scream means you're connected to anywhere, to anyone riding the same Internet circuit from Turkey, Greenland, Peru, or Nova Scotia. So you put out a general question and you wait. Computer communication is not much like most human communication. There's no body language, no intonation, no facial expression to help you know which way something ambiguous is meant. That's great reads the same on Internet as, oh, that's great. So the isolated communicators of cyberspace have come up with little signs made out of punctuation marks. They're called Emoticons. They go at the end of sentences as graphic explanations. They come out sideways. Tilt your head left and you'll see a little smiley face that means I'm kidding. A little frowny face that means I'm serious. Magazines, newspapers, television programs have started to take notice, and the coverage has led to an explosion of interest. The Internet is growing like an embryonic brain at a rate of 10% a month. It's all pure, clear, free, unregulated communication, although some of the regulators are thinking about changing that. U.S. congressional hearings into the Internet begin next month. Here in Canada, nothing yet. Borders still count for something. For CBC Primetime News, I'm Bill Cameron in Toronto.
So you have something there, thinking again from the 90s, of what people viewed the anonymous nature. And it's kind of funny for us to see what we have today versus what could predicted before as more people adopt it, but how we're using it. What does it mean for cultures? Are they defined geographically, or where is this virtual side and this engagement? And what is that difference between what we'd say virtual world and physical world, and even that beginning discussion with other people? And maybe it opens up world of connection for other people and how they communicate and what we have. Like this change of technology and this merge where we are at now. And again, this is just a news article from 1993 in this beginning of the public side where we are in this electrical world. Electrical computer machine.
Evolution.
So if we're looking to that beyond just the internet for stuff, of starting earlier on the internet and then the development of the WWW, so the World Wide Web, and the protocols where we're having new ideas of, even before this, of programming languages, of ways of encoding that go beyond ones and zeros and punch cards, but a physical language as a development, as a way to encode that people have skills. Like we had from that Jacquard loom and people learning of how to encode it in those cards versus people who were coding it here. And what does it mean to do that work in that field? And the web development now, and there's a wide range of stuff and new protocols of ways that computers can communicate as information and beginning points. And so Tim Berners-Lee is credited with being part of the beginning group of creating the idea of the World Wide Web and the standards. And this is in 91. And so it's simple protocol, platform independent from what you're working with. This is where you're starting to get the idea of hypertext for people who've done web development and your HTML tags. And you have information, communication, and entertainment being used. And so easy to use, useful, fun, whatever we want from it, where we are at. You're getting political things where it may not play a role coming in that could shape to where we are today, to businesses, to governments, to people, and that shifting forms of where we sit to where we actually could be. And then how does it affect us as a society? Because I'd say, like, again, now we're opening up, if we think about that data, information, knowledge, wisdom kind of pyramid, is that data and how we're receiving stuff comes to us differently now. So where our knowledge is and what's common sense starts shifting between generations, between people, between what we're using, who's exposed to what. Getting into the 2000s, as I speed this up because I don't want to make this forever, we're almost hitting like 2 hours for this lecture already. Is like, what about the idea of shifting from networks to wireless networks, and what we expect today to faster wireless networks and interconnections, and the speed of what we can do, and what can it be now, the conversion of non-physical connections of materials and networks and devices and like, you know, distributed networks of devices and the IoT and your home devices and everything else. And what will that mean? Your smartphones and what people have access to, which is still just a fast computer, but having access to this, but that everyone has access to this. New versions of what the web could actually be. What we're used to in the 2000s too, of like text messaging coming to play for communication, and cell phones and streaming videos starting, and where we're at now, even me being able to use this for you to give easy access. And we're getting like digitization of information and knowledge and everything we have now beyond a new rate. I was like, how does this change things once we have digitization? So taking real world objects, so image and sound documents, and turning that into a digital format. Creating digital representations of encoding that ones and zeros, manipulating and transmitting the information, and recreating in real-world objects that we're decoding this into 3D printers and your displays and sound and audio and everything we're used to, which is where we started this whole lecture of that information technology, which has always been there from that beginning time. This has always been there. It's just the materials and speed and what we can do, but how does it shift? Like even nowadays when we worry about digitization, what does it mean that we can do that easily reproduce stuff easily now from anybody, maintaining access and rights to stuff, to changing stuff for the future, what could be going from here? Like, how does digitization change things? What does it allow access to? What do people to expect? What becomes common sense? What can you do? How do people then react? And then where are we today? Like, what about today? How are things different? Like, what is expected here? And some people may be automatically jumping into this and recognizing an image like this from like NFTs, which I just like brought in for more comedic relief, but does connect to some people that this image itself could mean something culturally and what it is. And how is that developing? Even the idea of digital currencies and like what it means for this new economics around it and what's happening, and people are spending time, and if there's environmental concerns and societal things and laws or whatever else has to develop around this. Like, where are we now today and where could we be in the future? But this whole development, and why this is more just a history thing and not answering those questions, but just where I wanted to start, where we go from before, and where you can get some of these views of technology being so progressive and changing by viewing, like even the way I've talked, what we've gone over this, looking at this, you're like, oh, it seems to be like, yeah, this is progressing at a bigger rate from before, but is it? Or has it been shifts in our acceptance of stuff? Is it technology that's been doing these shift of having these new devices that then allowed for other things within a shift society? What was the societal roles and like who developed stuff and where are we now? And the digitalization, so where is it shifted? And so it's why I wanted to do this little bit of prehistory, but realizing that throughout all of it, we've had that information technology. We've had that encoding and decoding and manipulation. We've had that shift of being what is a computer from person to machine and mechanical, and moving parts to electronics and become the dominance, and the cheap manufacturing and that what causes issues and the backlog of this. So, and where we are now. And so again, what is common sense today is not what was common sense before, and what was wisdom and knowledge of where you would go. New fields of what came out of this and how we have shifted. So what interplay of the two roles of has this actually played? And maybe not taking for granted what you just see now today, but maybe questioning, well, why do I think this? Why is this common knowledge? Could this shift? For my age now, how will it shift for people who are younger than me that may have other experiences, for other cultures who haven't gone through the same thing? And what does this do? And where could we go? Good or bad or negative or neutral, whatever, from there. Because look at this vision right here. This is theoretically, this is just a joke picture. It's not a real one. But the first home computer is depicted by Popular Mechanics 1950. It's not real. This is just a meme picture. But like where we were, what we thought, what we could predict, and where it could be, and beyond just the functional capabilities of what we ever thought from those machines, is that there's way more that went in development culturally and economically for the development, acceptance, and change, and even being the idea of neutral tools and that progress kind of factor of where we were actually going to where we are today, where we are right now. So this is now ending off this part of the notes in history, and your reading for this week is chapter 13 from Diamond's book, and you're looking at chapter 13, so Necessity's Mother, in Guns, Germs, and Steel, The Fates of Human and Society. And now this is looking at the idea that necessity is the mother of invention, and why we got this is we needed this, so that's why it came out. Or was there more that came into this as this role? And while you're going through these notes, or you're thinking and you're going through the actual reading, here's some questions to think about. Like, why do Eurasians consider themselves superior to other people in terms of inventiveness and intelligence? So this comes from that Darwinian, social Darwinian kind of thing, and coming from Europe and that view from other cultures, what's inventiveness? Why was that there? Like here. Why is the hero myth of invention so attractive? Like this great creation of when we needed it. Why do we have that? Why is this inaccurate for the real reason of why we came to this point? It was really the need, and we need this, and this was made, and it was solved and invented, versus was there something else that went on? While war and trade lead people to develop new technologies, what other motivations have there been? Like, what other things, creations have there been? Is it always just this economic, or is there something beyond it? Is computer science just a field for industry and that's why you're losing it, or is it something else for the way that you understand? And what other motivations have there been? Why aren't all new inventions adopted? If they're so new and they're so great and they could be better than what's there before, what other factors played a role into this? Is there something else? And where do inventions actually come from? Is necessity the mother invention, or are the other sources of inspiration that are more important? So as usual in a bit here, I'm going to do the text-to-speech. So you can stop now if you're happy with everything, and you can go on Free Mary Worlds and read this on your own. Otherwise, I'm going to start the usual text-to-speech on this. But I hope over this last roughly 2 hours of this, you've gotten a rough feel of the shift of stuff of like computer technology and other things shifting within society that could be playing an impact for roles or whatever else. And I just hope that no matter beyond electronical mechanical devices, that through my digitally encoded voice and representation that you're listening to in the future, that you are doing okay. Like, I hope that you're okay. And I'm always trying to end these messages, and it's weird, but it's just that hope of using these devices, using everything else, just to say, like, I hope that you're okay and moving forwards. That no matter what grades you get or where you are, like, you're a developing person, that we are all flawed in some way, and we're just trying to learn and come together. And that include myself, and as I just try to learn, but making sure that I want to say that the people are important, and this is just a tool that I'm using to transmit this, and I think that you are important. If you don't think you're important, again, I'll say, you're wrong, I'm the teacher, I'm right, you are important. Everyone has an impact in some way within this actual world, good or bad, whatever, but if you want to move forwards and you're feeling down, I don't know. I just want to say that you're okay. Okay, so I'll stop blathering as I always do there, and you can stop here. Otherwise, you're going to see this pause, and then when it comes back in a second, from here I'll switch to the normal natural reader, and it'll start stepping through the reading. Otherwise, continue having a great day, and then think about these questions. They are important. Okay, welcome back. We're now on Chapter 13, Necessity's Mother, from the Diamond book. So you should have access to the entire book. So now this will just be a text-to-read speech of the actual Chapter 13. So we'll just zoom in the text, make it easier to follow along with the video if you're reading this, and then I'm going to turn off my microphone in a second, and then it'll go, and I will stop it at the end of the chapter.
Necessity's Mother. On July 3, 1908, archaeologists excavating the ancient Minoan palace at Phaistos, on the island of Crete, chanced upon one of the most remarkable objects in the history of technology. At first glance it seemed unprepossessing, just a small, flat, unpainted, circular disc of hard-baked clay, 6 feet 2 inches in diameter. Closer examination showed each side to be covered with writing, resting on a curved line that spiraled clockwise in 5 coils from the disc's rim to its center. A total of 241 signs or letters was neatly divided by etched vertical lines into groups of several signs, possibly constituting words. The writer must have planned and executed the disc with care, so as to start writing at the rim and fill up all the available space along a spiraling line, yet not run out of space on reaching the center. Ever since it was unearthed, the disc has posed a mystery for historians of writing. The number of distinct signs suggests a syllabary rather than an alphabet, but it is still undeciphered, and the forms of the signs are unlike those of any other known writing system. Not another scrap of the strange script has turned up in the 89 years since its discovery. Thus, it remains unknown whether it represents an indigenous Cretan script or a foreign import to Crete. One side of the two-sided Phaistos disk. Estimated date of 1700 BC makes it by far the earliest printed document in the world. Instead of being etched by hand, as were all texts of Crete's later Linear A and Linear B scripts, the disk signs were punched into soft clay by stamps that bore a sign as raised type. The printer evidently had a set of at least 45 stamps, one for each sign appearing on the disk. Making these stamps must have entailed a great deal of work, and they surely weren't manufactured just to print this single document. Whoever used them was presumably doing a lot of writing. With those stamps, their owner could make copies much more quickly and neatly than if he or she had written out each of the script's complicated signs at each appearance. The Phaistos disk anticipates humanity's next efforts at printing, which similarly used cut type or blocks but applied them to paper with ink, not to clay without ink. However, those next efforts did not appear until 2,500 years later in China and 3,100 years later in medieval Europe. Why was the disk's precocious technology not widely adopted in Crete or elsewhere in the ancient Mediterranean? Why was its printing method invented around 1700 BC in Crete and not at some other time in Mesopotamia, Mexico, or any other ancient center of writing? Why did it then take thousands of years to add the ideas of ink and a press and arrive at a printing press? The disk thus constitutes a threatening challenge to historians. If inventions are as idiosyncratic and unpredictable as the disk seems to suggest, then efforts to generalize about the history of technology may be doomed from the outset. Technology, in the form of weapons and transport, provides the direct means by which certain peoples have expanded their realms and conquered other peoples. That makes it the leading cause of history's broadest pattern. But why were Eurasians, rather than Native Americans or Sub-Saharan Africans, the ones to invent firearms, ocean-going ships, and steel equipment? The differences extend to most other significant technological advances, from printing presses to glass and steam engines. Why were all those inventions Eurasian? Why were all New Guineans and native Australians in Anno Domini 1800 still using stone tools like ones discarded thousands of years ago in Eurasia and most of Africa? Even though some of the world's richest copper and iron deposits are in New Guinea and Australia, respectively, all those facts explain why so many layered people assume that Eurasians are superior to other peoples in inventiveness and intelligence. If, on the other hand, no such difference in human neurobiology exists to account for continental differences in technological development, what does account for them? An alternative view rests on the heroic theory of invention. Technological advances seem to come disproportionately from a few very rare geniuses, such as Johann Gutenberg, James Watt, Thomas Edison, and the Wright brothers. They were Europeans, or descendants of European emigrants to America. So were Archimedes and other rare geniuses of ancient times. Could such geniuses have equally well been born in Tasmania or Namibia? Does the history of technology depend on nothing more than accidents of the birthplaces of a few inventors? Still another alternative view holds that it is a matter not of individual inventiveness but of the receptivity of whole societies to innovation. Some societies seem hopelessly conservative, inward-looking, and hostile to change. That's the impression of many Westerners who have attempted to help third world peoples and ended up discouraged. The people seem perfectly intelligent as individuals. The problem seems instead to lie with their societies. How else can one explain why the Aborigines of northeastern Australia failed to adopt bows and arrows, which they saw being used by Torres Straits Islanders with whom they traded? Might all the societies of an entire continent be unreceptive, thereby explaining technology's slow pace of development there? In this chapter we shall finally come to grips with the central problem of this book, the question of why technology did evolve at such different rates on different continents. The starting point for our discussion is the common view expressed in the saying necessity is the mother of invention. That is, invention supposedly arises when a society has an unfulfilled need. Some technology is widely recognized to be unsatisfactory or limiting. Would-be inventors, motivated by the prospect of money or fame, perceive the need and try to meet it. Some inventor finally comes up with a solution superior to the existing, unsatisfactory technology. Society adopts the solution if it is compatible with the society's values and other technologies. Quite a few inventions do conform to this common-sense view of necessity as invention's mother. In 1942, in the middle of World War II, the US government set up the Manhattan Project with the explicit goal of inventing the technology required to build an atomic bomb before Nazi Germany could do so. That project succeeded in 3 years, at a cost of $2 billion. Other instances are Eli Whitney's 1794 invention of his cotton gin to replace laborious hand cleaning of cotton grown in the U.S. South, and James Watt's 1769 invention of his steam engine to solve the problem of pumping water out of British coal mines. These familiar examples deceive us into assuming that other major inventions were also responses to perceived needs. In fact, many almost inventions were developed by people driven by curiosity or by a love of tinkering, in the absence of any initial demand for the product they had in mind. Once a device had been invented, the inventor then had to find an application for it. Only after it had been in use for a considerable time did consumers come to feel that they needed it. Still other devices, invented to serve one purpose, eventually found most of their use for other, unique, it-pated purposes. It may come as a surprise to learn that these inventions in search of a use include most of the major technological breakthroughs of modern times, ranging from the airplane and automobile, through the internal combustion engine and electric light bulb, to the phonograph and transistor. Thus, invention is often the mother of necessity, rather than vice versa. A good example is the history of Thomas Edison's phonograph, the most original invention of the greatest inventor of modern times. When Edison built his first phonograph in 1877, he published an article proposing 10 uses to which his invention might be put. They included preserving the last words of dying people, recording books for blind people to hear, announcing clock time, and teaching spelling. Reproduction of music was not high on Edison's list of priorities. A few years later Edison told his assistant that his invention had no commercial value. Within another few years he changed his mind and did enter business to sell phonographs, but for use as office dictating machines. When other entrepreneurs created jukeboxes by arranging for a phonograph to play popular music at the drop of a coin, Edison objected to this debasement, which apparently detracted from serious office use of his invention. Only after about 20 years did Edison reluctantly concede that the main use of his phonograph was to record and play music. The motor vehicle is another invention whose uses seem obvious today. However, it was not invented in response to any demand. When Nicolaus Otto built his first gas engine, in 1866, horses had been supplying people's land transportation needs for nearly 6,000 years, supplemented increasingly by steam-powered railroads for several decades. There was no crisis in the availability of horses, no dissatisfaction with railroads. Because Otto's engine was weak, heavy, and 7 feet tall, it did not recommend itself over horses. Not until 1885 did engines improve to the point that Gottfried Daimler got around to installing one on a bicycle to create the first motorcycle. He waited until 1896 to build the first truck. In 1905, motor vehicles were still expensive, unreliable toys for the rich. Public contentment with horses and railroads remained high until World War I, when the military concluded that it really did need trucks. Intensive post-war lobbying by truck manufacturers and armies finally convinced the public of its own needs and enabled trucks to begin to supplant horse-drawn wagons in industrialized countries. Even in the largest American cities, the changeover took 50 years. 244. Guns, germs, and steel. Inventors often have to persist at their tinkering for a long time in the absence of public demand, because early models performed too poorly to be useful. The first cameras, typewriters, and television sets were as awful as Otto's 7-foot-tall gas engine. That makes it difficult for an inventor to foresee whether his or her awful prototype might eventually find a use and thus warrant more time and expense to develop it. Each year, the United States issues about 70,000 patents, only a few of which ultimately reach the stage of commercial production. For each great invention that ultimately found a use, there are countless others that did not. Even inventions that meet the need for which they were initially designed may later prove more valuable at meeting unforeseen needs. While James Watt designed his steam engine to pump water from mines, it soon was supplying power to cotton mills, then propelling locomotives and boats. Thus, the common-sense view of invention that served as our starting point reverses the usual roles of invention and need. It also overstates the importance of rare geniuses, such as Watt and Edison. That heroic theory of invention, as it is termed, is encouraged by patent law, because an applicant for a patent must prove the novelty of the invention submitted. Inventors thereby have a financial incentive to denigrate or ignore previous work. From a patent lawyer's perspective, the ideal invention is one that arises without any precursors, like Aten springing fully formed from the forehead of Zeus. In reality, even for the most famous and apparently decisive modern inventions, neglected precursors lurked behind the bald claim X invented Y. For instance, we are regularly told, James Watt invented the steam engine in 1769, supposedly inspired by watching steam rise from a tea kettle spout. Unfortunately for this splendid fiction, Watt actually got the idea for a particular steam engine while repairing a model of Thomas Newcomen's steam engine, which Newcomen had invented 57 years earlier and of which over 100 had been manufactured in England by the time of Watt's repair work. Newcomen's engine, in turn, followed the steam engine that the Englishman Thomas Savery patented in 1698, which followed the steam engine that the Frenchman Denis Papin designed around 1680, which in turn had precursors in the ideas of the Dutch scientist Christiaan Huygens and others. All this is not to deny that Watt greatly improved Newcomen's engine, just as Newcomen had greatly improved Savery's. Similar histories can be related for all modern inventions that are adequately documented. The hero customarily credited with the invention followed previous inventors who had had similar aims and had already produced designs, working models, or commercially successful models. Edison and famous invention of the incandescent light bulb on the night of October 21, 1879, improved on many other incandescent light bulbs patented by other inventors between 1841 and 1878. Similarly, the Wright brothers' manned-powered airplane was preceded by the manned-unpowered gliders of Otto Lilienthal and the unmanned-powered airplane of Samuel Langley. Samuel Morse's telegraph was preceded by those of Joseph Henry, William Cooke, and Charles Wheatstone, and Eli Whitney's gin for cleaning short staple cotton extended gins that had been cleaning long stale cotton for thousands of years. All this is not to deny that Watt, Edison, the Wright brothers, Morse, and Whitney made big improvements and thereby increased or inaugurated commercial success. The form of the invention eventually adopted might have been somewhat different without the recognized inventor's contribution. But the question for our purposes is whether the broad pattern of world history would have been altered significantly if some genius inventor had not been born at a particular place and time. The answer is clear: there has never been any such person. All recognized famous inventors had capable predecessors and successors and made their improvements at a time when society was capable of using their product. As we shall see, the tragedy of the hero who perfected the stamps used for the Phaistos disc was that he or she devised something that the society of the time could not exploit on a large scale. Examples so far have been drawn from modern technologies, because their histories are well known. My two main conclusions are that technology develops cumulatively, rather than in isolated heroic acts, and that it finds most of its uses after it has been invented, rather than being invented to meet a foreseen need. These conclusions surely apply with much greater force to the undocumented history of ancient technology. When Ice Age hunter-gatherers noticed burnt sand and limestone residues in their hearths, it was impossible for them to foresee the long, serendipitous accumulation of discoveries that would lead to the first Roman glass windows, by way of the first objects with surface glazes, the first freestanding glass objects of Egypt and Mesopotamia, and the first glass vessels around 1500 BC. We know nothing about how those earliest known surface glazes themselves were developed. Nevertheless, we can infer the methods of prehistoric invention by watching technologically primitive people today, such as the New Guineans with whom I work. I already mentioned their knowledge of hundreds of local plant and animal species and each species' edibility, medical value, and other uses. New Guineans told me similarly about dozens of rock types in their environment and each type's hardness, color, behavior when struck or flaked, and uses. All of that knowledge is acquired by observation and by trial and error. I see that process of invention going on whenever I take New Guineans to work with me in an area away from their homes. They constantly pick up unfamiliar things in the forest, tinker with them, and occasionally find them useful enough to bring home. I see the same process when I am abandoning a campsite, and local people come to scavenge what is left. They play with my discarded objects and try to figure out whether they might be useful in New Guinea society. Discarded tin cans are easy, they end up reused as containers. Other objects are tested for purposes very different from the one for which they were manufactured. How would that yellow number 2 pencil look as an ornament, inserted through a pierced earlobe or nasal septum? Is that piece of broken glass sufficiently sharp and strong to be useful as a knife? Eureka! The raw substances available to ancient peoples were natural materials such as stone, wood, bone, skins, fiber, clay, sand, limestone, and minerals, all existing in great variety. From those materials, people gradually learned to work particular types of stone, wood, and bone into tools, to convert particular clays into pottery and bricks, to convert certain mixtures of sand, limestone, and other dirt into glass, and to work available pure soft metals such as copper and gold, then to extract metals from ores, and finally to work hard metals such as bronze and iron. A good illustration of the histories of trial and error involved is furnished by the development of gunpowder and gasoline from raw materials. Combustible natural products inevitably make themselves noticed, as when a resinous log explodes in a campfire. By 2000 BC, Mesopotamians were extracting tons of petroleum by heating rock asphalt. Ancient Greeks discovered the uses of various mixtures of petroleum, pitch, resins, sulfur, and quicklime as incendiary weapons, delivered by catapults, arrows, firebombs, and ships. The expertise at distillation that medieval Islamic alchemists developed to produce alcohols and perfumes also let them distill petroleum into fractions, some of which proved to be even more powerful incendiaries. Delivered in grenades, rockets, and torpedoes, those incendiaries played a key role in Islam's eventual defeat of the Crusaders. By then, the Chinese had observed that a particular mixture of sulfur, charcoal, and saltpeter, which became known as gunpowder, was especially explosive. An Islamic chemical treatise of about Anno Domini 1100 describes 7 gunpowder recipes, while a treatise from Anno Domini 1280 gives more than 70 recipes that had proved suitable for diverse purposes. As for post-medieval petroleum distillation, 19th century chemists found the middle distillate fraction useful as fuel for oil lamps. The chemists discarded the most volatile fraction as an unfortunate waste product, until it was found to be an ideal fuel for internal combustion engines. Who today remembers that gasoline, the fuel of modern civilization, originated as yet another invention in search of a use? Once an inventor has discovered a use for a new technology, the next step is to persuade society to adopt it. Merely having a bigger, faster, more powerful device for doing something is no guarantee of ready acceptance. Innumerable such technologies were either not adopted at all or adopted only after prolonged resistance. Notorious examples include the US Congress's rejection of funds to develop a supersonic transport in 1971, the world's continued rejection of an efficiently designed typewriter keyboard, and Britain's long reluctance to adopt electric lighting. What is it that promotes an invention's acceptance by a society? Let's begin by comparing the acceptability of different inventions within the same society. It turns out that at least 4 factors influence acceptance. The first and most obvious factor is relative economic advantage. Paired with existing technology. While wheels are very useful in modern industrial societies, that has not been so in some other societies. Ancient native Mexicans invented wheeled vehicles with axles for use as toys, but not for transport. That seems incredible to us, until we reflect that ancient Mexicans lacked domestic animals to hitch to their wheeled vehicles, which therefore offered no advantage over human porters. A second consideration is social value and prestige, which can override economic benefit. Millions of people today buy designer jeans for double the price of equally durable generic jeans, because the social cachet of the designer label counts for more than the extra cost. Similarly, Japan continues to use its horrendously cumbersome kanji writing system in preference to efficient alphabets or Japan's own efficient kana syllabary, because the prestige attached to kanji is so great. Still another factor is compatibility with vested interests. This book, like probably every other typed document you have ever read, was typed with a QWERTY keyboard, named for the leftmost 6 letters in its upper row. Unbelievable as it may now sound, the keyboard layout was designed in 1873 as a feat of anti-engineering. It employs a whole series of perverse tricks designed to force typists to type as slowly as possible, such as scattering the commonest letters over all keyboard rows and concentrating them on the left side. The reason behind all of those seemingly counterproductive features is that the typewriters of 1873 jammed if adjacent keys were struck in quick succession, so that manufacturers had to slow down typists. When improvements in typewriters eliminated the problem of jamming, trials in 1932 with an efficiently laid-out keyboard showed that it would let us double our typing speed and reduce our typing effort by 95%. But QWERTY keyboards were solidly entrenched by then. The vested interests of hundreds of millions of QWERTY typists, typing teachers, typewriter and computer salespeople, and manufacturers have crushed all moves toward keyboard efficiency for over 60 years. While the story of the QWERTY keyboard may sound funny, many similar cases have involved much heavier economic consequences. Why does Japan now dominate the world market for transistorized electronic consumer products, to a degree that damages the United States' balance of payments with Japan? Even though transistors were invented and patented in the United States, because Sony bought transistor licensing rights from Western Electric at a time when the American electronics consumer industry was churning out vacuum tube models and reluctant to compete with its own products. Why were British cities still using gas street lighting into the 1920s? long after US and German cities had converted to electric street lighting. Because British municipal governments had invested heavily in gas lighting and placed regulatory obstacles in the way of the competing electric light companies. The remaining consideration affecting acceptance of new technologies is the ease with which their advantages can be observed. In Anno Domini 1340, when firearms had not yet reached most of Europe, England's Earl of Derby and Earl of Salisbury happened to be present in Spain at the Battle of Tarifa, where Arabs used cannons against the Spaniards. Impressed by what they saw, the Earls introduced cannons to the English army, which adopted them enthusiastically and already used them against French soldiers at the Battle of Crecy 6 years later. Thus, wheels, designer genes, and QWERTY keyboards illustrate the varied reasons why the same society is not equally receptive to all inventions. Conversely, the same invention's reception also varies greatly among contemporary societies. We are all familiar with the supposed generalization that rural third world societies are less receptive to innovation than our westernized industrial societies. Even within the industrialized world, some areas are much more receptive than others. Such differences, if they existed on the continental scale, might explain why technology developed faster on some continents than on others. For instance, if all Aboriginal Australian societies were for some reason uniformly resistant to change, that might account for their continued use of stone tools after metal tools had appeared on every other continent. How do differences in receptivity among societies arise? A laundry list of at least 14 explanatory factors has been proposed by historians of technology. One is long life expectancy, which in principle should give prospective inventors the years necessary to accumulate technical knowledge, as well as the patience and security to embark on long development programs yielding delayed rewards. Hence the greatly increased life expectancy brought by modern medicine may have contributed to the recently accelerating pace of invention. The next 5 factors involve economics or the organization of society. The availability of cheap slave labor in classical times supposedly dies. Encouraged innovation then, whereas high wages or labor scarcity now stimulate the search for technological solutions. For example, the prospect of changed immigration policies that would cut off the supply of cheap Mexican seasonal labor to Californian farms was the immediate incentive for the development of a machine-harvestable variety of tomatoes in California. Patents and other property laws, protecting ownership rights of inventors, reward innovation in the modern West, while the lack of such protection discourages it in modern China. Modern industrial societies provide extensive opportunities for technical training, as medieval Islam did and modern Zaire does not. Modern capitalism is, and the ancient Roman economy was not, organized in a way that made it potentially rewarding to invest capital in technological development. The strong individualism of US society allows successful inventors to keep earnings for themselves. Whereas strong family ties in New Guinea ensure that someone who begins to earn money will be joined by a dozen relatives expecting to move in and be fed and supported. Another 4 suggested explanations are ideological, rather than economic or organizational. Risk-taking behavior, essential for efforts at innovation, is more widespread in some societies than in others. The scientific outlook is a unique feature of post-Renaissance European society that has contributed heavily to its modern technological preeminence. Tolerance of diverse views and of heretics fosters innovation, whereas a strongly traditional outlook stifles it. Religions vary greatly in their relation to technological innovation. Some branches of Judaism and Christianity are claimed to be especially compatible with it, while some branches of Islam, Hinduism, and Brahmanism may be especially incompatible with it. All 10 of these hypotheses are plausible, but none of them has any necessary association with geography. If patent rights, capitalism, and certain religions do promote technology, what's selected for those factors in post-medieval Europe, but not in contemporary China or India? At least the direction in which those 10 factors influence technology seems clear. The remaining 4 proposed factors, war, centralized government, climate, and resource abundance, appear to act inconsistently. Sometimes they stimulate technology, sometimes they inhibit it. Throughout history, war has often been a leading stimulant of technological innovation. For instance, the enormous investments made in nuclear weapons during World War II and in airplanes and trucks during World War I launched whole new fields of technology. But wars can also deal devastating setbacks to technological development. Strong centralized government boosted technology in late 19th century Germany and Japan, and crushed it in China after Anno Domini 1500. Many Northern Europeans assume that technology thrives in a rigorous climate where survival is impossible without technology, and withers in a benign climate where clothing is unnecessary and bananas supposedly fall off the trees. An opposite view is that benign environments leave people free from the constant struggle for existence, free to devote themselves to innovation. There has also been debate over whether technology is stimulated by abundance or by scarcity of environmental resources. Abundant resources might stimulate the development of inventions utilizing those resources, such as watermill technology in rainy northern Europe. With its many rivers, but why didn't watermill technology progress more rapidly in even rainier New Guinea? The destruction of Britain's forests has been suggested as the reason behind its early lead in developing coal technology. But why didn't deforestation have the same effect in China? This discussion does not exhaust the list of reasons proposed to explain why societies differ in their receptivity to new technology. Worse yet, all of these proximate explanations bypass the question of the ultimate factors behind them. This may seem like a discouraging setback in our attempt to understand the course of history, since technology has undoubtedly been one of history's strongest forces. However, I shall now argue that the diversity of independent factors behind technological innovation actually makes it easier, not harder, to understand history's broad pattern. For the purposes of this book, the key question about the laundry list is whether such factors differed systematically from continent to continent and thereby led to continental differences in technological development. Most lay people and many historians assume, expressly or tacitly, that the answer is yes. For example, it is widely believed that Australian Aborigines as a group shared ideological characteristics contributing to their technological backwardness. They were supposedly conservative, living in an imagined past REM time of the world's creation, and not focused on practical ways to improve the present. A leading historian of Africa characterized Africans as inward-looking and lacking Europeans' drive for expansion. But all such claims are based on pure speculation. There has never been a study of many societies under similar socio-economic conditions on each of two continents, demonstrating systematic ideological differences between the two continents' peoples. The usual reasoning is instead circular, because technological differences exist, the existence of corresponding ideological differences is inferred. In reality, I regularly observe in New Guinea that native societies there differ greatly from each other in their prevalent outlooks. Just like industrialized Europe and America, traditional New Guinea has conservative societies that resist new ways, living side by side with innovative societies that selectively adopt new ways. The result, with the arrival of Western technology, is that the more entrepreneurial societies are now exploiting Western technology to overwhelm their conservative neighbors. For example, when Europeans first reached the highlands of eastern New Guinea, in the 1930s, they discovered dozens of previously uncontacted Stone Age tribes, of which the Chimbu tribe proved especially aggressive in adopting Western technology. When Chimbas saw white settlers planting coffee, they began growing coffee themselves as a cash crop. In 1964 I met a 50-year-old Chimbu man, unable to read, wearing a traditional grass skirt, and born into a society still using stone tools, who had become rich by growing coffee, used his profits to buy a sawmill for $100,000 cash, and bought a fleet of trucks to transport his coffee and timber to market. In contrast, a neighboring highland people with whom I worked for 8 years, the Daribai, are especially conservative and uninterested in new technology. When the first helicopter landed in the Daribai area, they briefly looked at it and just went back to what they had been doing. The Chimbas would have been bargaining to charter it. As a result, Chimbas are now moving into the Daribai area, taking it over for plantations, and reducing the Daribai to working for them. On every other continent as well, certain native societies have proved very receptive, adopted foreign ways and technology selectively, and integrated them successfully into their own society. In Nigeria, the Igbo people became the local entrepreneurial equivalent of New Guinea's Chimbas. Today the most numerous Native American tribe in the United States is the Navajo, who on European arrival were just one of several hundred tribes. But the Navajo proved especially resilient and able to deal selectively with innovation. They incorporated Western dyes into their weave, became silversmiths and ranchers, and now drive trucks while continuing to live in traditional dwellings. Among the supposedly conservative Aboriginal Australians as well, there are receptive societies along with conservative ones. At the one extreme, the Tasmanians continued to use stone tools superseded tens of thousands of years earlier in Europe and replaced in most of mainland Australia too. At the opposite extreme, some Aboriginal fishing groups of southeastern Australia devised elaborate technologies for managing fish populations, including the construction of canals, weirs, and standing traps. Thus, the development and reception of inventions vary enormously from society to society on the same continent. They also vary over time within the same society. Nowadays, Islamic societies in the Middle East are relatively conservative and not at the forefront of technology. But medieval Islam in the same region was technologically advanced and open to innovation. It achieved far higher literacy rates than contemporary Europe. It assimilated the legacy of classical Greek civilization to such a degree that many classical Greek books are now known to us only through Arabic copies. It invented or elaborated windmills, tidal mills, trigonometry, and lateen sails. It made major advances in metallurgy, mechanical and chemical engineering, and irrigation methods, and it adopted paper and gunpowder from China and transmitted them to Europe. In the Middle Ages the flow of technology was overwhelmingly from Islam to Europe, rather than from Europe to Islam as it is today. Only after around Anno Domini 1500 did the net direction of flow begin to reverse. Innovation in China too fluctuated markedly with time. Until around Anno Domini 1450, China was technologically much more innovative and advanced than Europe, even more so than medieval Islam. The long list of Chinese inventions includes canal lock gates, cast iron, deep drilling, efficient animal harnesses, gunpowder, kites, magnetic compasses, movable type, paper, porcelain, printing, steam-post rudders, and wheelbarrows. China then ceased to be innovative for reasons about which we shall speculate in the epilogue. Conversely, we think of Western Europe and its derived North American societies as leading the modern world in technological innovation. But technology was less advanced in Western Europe than in any other civilized area of the Old World until the late Middle Ages. Thus, it is untrue that there are continents whose societies have tended to be innovative and continents whose societies have tended to be conservative. On any continent, at any given time, there are innovative societies and also conservative ones. In addition, receptivity to innovation fluctuates in time within the same region. On reflection, these conclusions are precisely what one would expect if a society's innovativeness is determined by many independent factors. Without a detailed knowledge of all of those factors, innovativeness becomes unpredictable. Hence social scientists continue to debate the specific reasons why receptivity changed in Islam, China, and Europe, and why the Chimbas, Ibos, and Navajo were more receptive to new technology than were their neighbors. To the student of broad historical patterns, though, it makes no difference what the specific reasons were in each of those cases. The myriad factors affecting innovativeness make the historian's task paradoxically easier, by converting societal variation in innovativeness into essentially a random variable. That means that, over a large enough area at any particular time, some proportion of societies is likely to be innovative. Where do innovations actually come from? For all societies except the few past ones that were completely isolated, much almost new technology is not invented locally but is instead borrowed from other societies. The relative importance of local invention and of borrowing depends mainly on two factors, these of invention of the particular technology, and the proximity of the particular society to other societies. Some inventions arose straightforwardly from the handling of natural raw materials. Such inventions developed on many independent occasions in world history, at different places and times. One example, which we have already considered at length, is plant domestication, with at least 9 independent origins. Another is pottery, which may have arisen from observations of the behavior of clay, a very widespread natural material, when dried or heated. Pottery appeared in Japan around 14,000 years ago, in the Fertile Crescent and China by around 10,000 years ago, and in Amazonia, Africa's Sahel Zone, the US Southeast, and Mexico thereafter. An example of a much more difficult invention is writing, which does not suggest itself by observation of any natural material. As we saw in Chapter 12, it had only a few independent origins, and the alphabet arose apparently only once in world history. Other difficult inventions include the water wheel, rotary quern, tooth gearing, magnetic compass, windmill, and camera obscura, all of which were invented only once or twice in the Old World and never in the New World. Such complex inventions were usually acquired by borrowing, because they spread more rapidly than they could be independently invented locally. A clear example is the wheel, which is first attested around 3400 BC near the Black Sea, and then turns up within the next few centuries over much of Europe and Asia. All those early Old World wheels are of a peculiar design, a solid wooden circle constructed of 3 planks fastened together, rather than a rim with spokes. In contrast, the saw wheels of Native American societies consisted of a single piece, suggesting a second independent invention of the wheel, as one would expect from other evidence for the isolation of New World from Old World civilizations. No one thinks that that same peculiar Old World wheel design appeared repeatedly by chance at many separate sites of the Old World within a few centuries of each other, after 7 million years of wheelless human history. Instead, the utility of the wheel surely caused it to diffuse rapidly east and west over the Old World from its sole site of invention. Other examples of complex technologies that diffused east and west in the ancient Old World, from a single West Asian source, include door locks, pulleys, rotary querns, windmills, and the alphabet. A New World example of technological diffusion is metallurgy, which spread from the Andes via Panama to Mesoamerica. When a widely useful invention does crop up in one society, it then tends to spread in either of two ways. One way is that other societies see or learn of the invention, are receptive to it, and adopt it. The second is that societies lacking the invention find themselves at a disadvantage vis-à-vis the inventing society, and they become overwhelmed and replaced if the disadvantage is sufficiently great. A simple example is the spread of muskets among New Zealand's Maori tribes. One tribe, the Ngāpuhi, adopted muskets from European traders around 1818. Over the course of the next 15 years, New Zealand was convulsed by the so-called musket wars, as musketless tribes either acquired muskets or were subjugated by tribes already armed with them. The outcome was that musket technology had spread throughout the whole of New Zealand by 1833, all surviving Maori tribes now had muskets. When societies do adopt a new technology from the society that invented it, the diffusion may occur in many different contexts. They include peaceful trade, espionage, emigration, and war. A crucial case of the last was the transfer of Chinese papermaking techniques to Islam, made possible when an Arab army defeated a Chinese army at the Battle of Talas River in Central Asia in Anno Domini 751, found some papermakers among the prisoners of war, and brought them to Samarkand to set up paper manufacture. In Chapter 12 we saw that cultural diffusion can involve either detailed blueprints or just vague ideas stimulating a reinvention of details. While Chapter 12 illustrated those alternatives for the spread of writing, they also apply to the diffusion of technology. The preceding paragraph gave examples of blueprint copying, whereas the transfer of Chinese porcelain technology to Europe provides an instance of long-drawn-out idea diffusion. Porcelain, a fine-grained translucent pottery, was invented in China around the 7th century Anno Domini. When it began to reach Europe by the Silk Road in the 14th century, it was much admired, and many unsuccessful attempts were made to imitate it. Not until 1707 did the German alchemist Johann Böttcher, after lengthy experiments with processes and with mixing various minerals and clays together, hit upon the solution and establish the now famous Meissen porcelain works. More or less independent later experiments in France and England led to Sevres, Wedgwood, and Spode porcelains. Thus, European potters had to reinvent Chinese manufacturing methods for themselves, but they were stimulated to do so by having models of the desired product before them. Depending on their geographic location, societies differ in how readily they can receive technology by diffusion from other societies. The most isolated people on Earth in recent history were the Aboriginal Tasmanians, living without ocean-going watercraft on an island 100 miles from Australia, itself the most isolated continent. The Tasmanians had no contact with other societies for 10,000 years and acquired no new technology other than what they invented themselves. Australians and New Guineans, separated from the Asian mainland by the Indonesian island chain, received only a trickle of inventions from Asia. The societies most accessible to receiving inventions by diffusion were those embedded in the major continents. In these societies technology developed most rapidly, because they accumulated not only their own inventions but also those of other societies. For example, medieval Islam, centrally located in Eurasia, acquired inventions from India and China and inherited ancient Greek learning. The importance of diffusion, and of geographic location in making it possible, is strikingly illustrated by some otherwise incomprehensible cases of societies that abandon powerful technologies. We tend to assume that useful technologies, once acquired, inevitably persist until superseded by better ones. In reality, technologies must be not only acquired but also maintained, and that too depends on many unpredictable factors. Any society goes through social movements or fads, in which economically useless things become valued or useful things devalued temporarily. Nowadays, when almost all societies on Earth are connected to each other, we cannot imagine fads going so far that an important technology would actually be discarded. A society that temporarily turned against a powerful technology would continue to see it being used by neighboring societies and would have the opportunity to acquire it by diffusion. But such fads can persist in isolated societies. A famous example involves Japan's abandonment of guns. Firearms reached Japan in Anno Domini 1543, when two Portuguese adventurers armed with harquebuses arrived on a Chinese cargo ship. The Japanese were so impressed by the new weapon that they commenced indigenous gun production, greatly improved gun technology, and by Anno Domini 1600 owned more and better guns than any other country in the world. But there were also factors working against the acceptance of firearms in Japan. The country had a numerous warrior class, the samurai, for whom swords rated as class symbols and works of art. Japanese warfare had previously involved single combats between samurai swordsmen, who stood in the open, made ritual speeches, and then took pride in fighting gracefully. Such behavior became lethal in the presence of peasant soldiers ungracefully blasting away with guns. In addition, guns were a foreign invention and grew to be despised, as did other things foreign in Japan after 1600. The samurai-controlled government began by restricting gun production to a few cities, then introduced a requirement of a government license for producing a gun, then issued licenses only for guns produced for the government, and finally reduced government orders for guns, until Japan was almost without functional guns again. Contemporary European rulers also included some who despised guns and tried to restrict their availability. But such measures never got far in Europe, where any country that temporarily swore off firearms would be promptly overrun by gun-toting neighboring countries. Only because Japan was a populous, isolated island could it get away with its rejection of the powerful new military technology. Its safety in isolation came to an end in 1853, when the visit of Commodore Perry's U.S. fleet bristling with cannons convinced Japan of its need to resume gun manufacture. That rejection and China's abandonment of ocean-going ships are well-known historical instances of technological reversals in isolated or semi-isolated societies. Other such reversals occurred in prehistoric times. The extreme case is that of Aboriginal Tasmanians, who abandoned even bone tools and fishing to become the society with the simplest technology in the modern world. Aboriginal Australians may have adopted and then abandoned bows and arrows. Torres Islanders abandoned canoes, while Giaua Islanders abandoned and then readopted them. Pottery was abandoned throughout Polynesia. Most Polynesians and many Melanesians abandoned the use of bows and arrows in war. Polar Eskimos lost the bow and arrow and the kayak, while Dorset Eskimos lost the bow and arrow, bow drill, and dogs. These examples, at first so bizarre to us, illustrate well the roles of geography and of diffusion in the history of technology. Without diffusion, fewer technologies are required, and more existing technologies are lost. Because technology begets more technology, the importance of an invention's diffusion potentially exceeds the importance of the original invention. Technology's history exemplifies what is termed an autocatalytic process, that is, one that speeds up at a rate that increases with time, because the process catalyzes itself. The explosion of technology since the Industrial Revolution impresses us today, but the medieval explosion was equally impressive compared with that of the Bronze Age, which in turn dwarfed that of the Upper Paleolithic. One reason why technology tends to catalyze itself is that advances depend upon previous mastery of simpler problems. For example, Stone Age farmers did not proceed directly to extracting and working iron, which requires high-temperature furnaces. Instead, iron or metallurgy grew out of thousands of years of human experience with natural outcrops of pure metals soft enough to be hammered into shape without heat. It also grew out of thousands of years of development of simple furnaces to make pottery, and then to extract copper ores and work copper alloys that do not require as high temperatures as does iron. In both the Fertile Crescent and China, iron objects became common only after about 2,000 years of experience of bronze metallurgy. New World societies had just begun making bronze artifacts and had not yet started making iron ones at the time when the arrival of Europeans truncated the New World's independent trajectory. The other main reason for autocatalysis is that new technologies and materials make it possible to generate still other new technologies by recombination. For instance, why did printing spread explosively in medieval Europe after Gutenberg printed his Bible in Anno Domini 1455? But not after that unknown printer printed the Phaistos disk in 1700 BC? The explanation is partly that medieval European printers were able to combine 6 technological advances, most of which were unavailable to the maker of the Phaistos disk. Of those advances, in paper, movable type, metallurgy, presses, inks, and scripts, paper and the idea of movable type reached Europe from China. Gutenberg's development of typecasting from metal dies, to overcome the potentially fatal problem of non-uniform type size, depended on many metallurgical developments: steel for letter punches, brass or bronze alloys for dies, lead for molds, and a tin-zinc lead alloy for type. Gutenberg's press was derived from screw presses in use for making wine and olive oil, while his ink was an oil-based improvement on existing inks. The alphabetic scripts that medieval Europe inherited from 3 millennia of alphabet development lent themselves to printing with movable type, because only a few dozen letter forms had to be cast, as opposed to the thousands of signs required for Chinese writing. In all 6 respects, The maker of the Phaistos disk had access to much less powerful technologies to combine into a printing system than did Gutenberg. The disk's writing medium was clay, which is much bulkier, 260 guns, germs, and steel, and heavier than paper. The metallurgical skills, inks, and presses of 1700 BC Crete were more primitive than those of Anno Domini 1455 Germany, so the disk had to be punched by hand rather than by cast mover type locked into a metal frame, inked, and pressed. The disk script was a syllabary with more signs, of more complex form, than the Roman alphabet used by Gutenberg. As a result, the Phaistos disk's printing technology was much clumsier, and offered fewer advantages over writing by hand, than Gutenberg's printing press. In addition to all those technological drawbacks, the Phaistos disk was printed at a time when knowledge of writing was confined to a few palace or temple scribes. Hence there was little demand for the disk maker's beautiful product, and little incentive to invest in making the dozens of hand punches required. In contrast, the potential mass market for printing in medieval Europe induced numerous investors to lend money to Gutenberg. Human technology developed from the first stone tools, in use by 2.5 million years ago, to the 1996 laser printer that replaced my already outdated 1992 laser printer and that was used to print this book's manuscript. The rate of development was undetectably slow at the beginning, when hundreds of thousands of years passed with no discernible change in our stone tools and with no surviving evidence for artifacts made of other materials. Today, technology advances so rapidly that it is reported in the daily newspaper. In this long history of accelerating development, one can single out two especially significant jumps. The first, occurring between 100,000 and 50,000 years ago, probably was made possible by genetic changes in our bodies, namely, by evolution of the modern anatomy permitting modern speech or modern brain function, or both. That jump led to bone tools, single-purpose stone tools, and compound tools. The second jump resulted from our adoption of a sedentary lifestyle, which happened at different times in different parts of the world, as early as 13,000 years ago in some areas and not even today in others. For the most part, that adoption was linked to our adoption of food production, which required us to remain close to our crops, orchards, and stored food surpluses. Sedentary living was decisive for the history of technology, because it enabled people to accumulate non-portable possessions. Nomadic hunter gatherers are limited to technology that can be carried. If you move often and lack vehicles or draft animals, you confine your possessions to babies, weapons, and a bare minimum of other absolute necessities small enough to carry. You can't be burdened with pottery and printing presses as you shift camp. That practical difficulty probably explains the tantalizingly early appearance of some technologies, followed by a long delay in their further development. For example, the earliest attested precursors of ceramics are fired clay figurines made in the area of modern Czechoslovakia 27,000 years ago, long before the oldest known fired clay vessels. The same area of Czechoslovakia at the same time has yielded the earliest evidence for weaving, otherwise not attested until the oldest known musket appears around 13,000 years ago and the oldest known woven cloth around 9,000 years ago. Despite these very early first steps, neither pottery nor weaving took off until people became sedentary and thereby escaped the problem of transporting pots and looms. Besides permitting sedentary living and hence the accumulation of possessions, food production was decisive in the history of technology for another reason. It became possible, for the first time in human evolution, to develop economically specialized societies consisting of non-food producing specialists fed by food-producing peasants. But we already saw, in part 2 of this book, that food production arose at different times in different continents. In addition, as we've seen in this chapter, local technology depends, for both its origin and its maintenance, not only on local invention but also on the diffusion of technology from elsewhere. That consideration tended to cause technology to develop most rapidly on continents with few geographic and ecological barriers to diffusion, either within that continent or on other continents. Finally, each society on a continent represents one more opportunity to invent and adopt a technology, because societies vary greatly in their innovativeness for many separate reasons. Hence, all other things being equal, technology develops fastest in large productive regions with large human populations, many potential inventors, and many competing societies. Let us now summarize how variations in these 3 factors, time of onset of food production, barriers to diffusion, and human population size, led straightforwardly to the observed intercontinental differences in the development of technology. Eurasia, effectively including North Africa, is the world's largest landmass, encompassing the largest number of competing societies. It was also the landmass with the two centers where food production began the earliest, the Fertile Crescent and China. Its east-west major axis permitted many inventions adopted in one part of Eurasia to spread relatively rapidly to societies at similar latitudes and climates elsewhere in Eurasia. Its breadth along its minor axis contrasts with the Americas' narrowness at the Isthmus of Panama. It lacks the severe ecological barriers transecting the major axes of the Americas and Africa. Thus, geographic and ecological barriers to diffusion of technology were less severe in Eurasia than in other continents. Thanks to all these factors, Eurasia was the continent on which technology started its post-Pleistocene acceleration earliest and resulted in the greatest local accumulation of technologies. North and South America are conventionally regarded as separate continents, but they have been connected for several million years, pose similar historical problems, and may be considered together for comparison with Eurasia. The Americas form the world's second largest landmass, significantly smaller than Eurasia. However, they are fragmented by geography and by ecology. The Isthmus of Panama, only 40 miles wide, virtually transects the Americas geographically, as do the Isthmus's Darien rainforests and the northern Mexican desert ecologically. The latter desert separated advanced human societies of Mesoamerica from those of North America, while the Isthmus separated advanced societies of Mesoamerica from those of the Andes and Amazonia. In addition, the main axis of the Americas is north-south, forcing most diffusion to go against a gradient of latitude rather than to operate within the same latitude. For example, wheels were invented in Mesoamerica, and llamas were domesticated in the Central Andes by 3000 BC, but 5,000 years later the Americas sole beast of burden and so wheels had still not encountered each other. Even though the distance separating Mesoamerica's Maya societies from the northern border of the Inca Empire was far less than the 6,000 miles separating wheel and horse-sharing France and China. Those factors seem to me to account for the Americas' technological lag behind Eurasia. Sub-Saharan Africa is the world's third largest landmass, considerably smaller than the Americas. Throughout most of human history it was far more accessible to Eurasia than were the Americas, but the Saharan Desert is still a major ecological barrier separating Sub-Saharan Africa from Eurasia plus North Africa. Africa's north-south axis posed a further obstacle to the diffusion of technology, both between Eurasia and Sub-Saharan Africa and within the Sub-Saharan region itself. As an illustration of the latter obstacle, pottery and iron metallurgy arose in or reached Sub-Saharan Africa's Sahel zone at least as early as they reached Western Europe. However, pottery did not reach the southern tip of Africa until around Anno Domini I, and metallurgy had not yet diffused overland to the southern tip by the time that it arrived there from Europe on ships. Finally, Australia is the smallest continent. The very low rainfall and productivity of most of Australia makes it effectively even smaller as regards its capacity to support human populations. It is also the most isolated continent. In addition, food production never arose indigenously in Australia. Those factors combined to leave Australia the sole continent still without metal artifacts in modern times. Table 13.1 translates these factors into numbers, by comparing the continents with respect to their areas and their modern human populations. The continent's populations 10,000 years ago, just before the rise of food production, are not known but surely stood in the same sequence, since many of the areas producing the most food today would also have been productive areas for hunter-gatherers 10,000 years ago. The differences in population are glaring. Eurasia's is nearly 6 times that of the Americas, nearly 8 times that of Africa's, and 230 times that of Australia's. Larger populations mean more inventors and more competing societies. Table 13.1 by itself goes a long way toward explaining the origins of guns and steel in Eurasia. All these effects that continental differences in area, population, ease of Table 13.1 human populations of the continents, diffusion, and onset of food production exerted on the rise of technology became exaggerated, because technology catalyzes itself. Eurasia's considerable initial advantage thereby was translated into a huge lead as of Anno Domini 1492, for reasons of Eurasia's distinctive geography rather than of distinctive human intellect. The New Guineans whom I know include potential Edsins. But they directed their ingenuity toward technological problems appropriate to their situations, the problems of surviving without any imported items in the New Guinea jungle, rather than the problem of inventing phonographs. Chapter 4.